If you open a modern artificial intelligence model and inspect its silicon circuits mid-thought, you will not find a single concept, fact, or line of reasoning. You will find only millions of floating point numbers streaming across graphics memory at terabytes per second, calculating geometric angles between words that have been transformed into points in an 8,000-dimensional space. How this purely mechanical symphony of matrix multiplications creates the illusion of a brilliant conversational partner is one of the most fascinating engineering triumphs in human history. To control this machinery with surgical precision rather than blind hope, you have to look beneath the conversational interface and understand the hidden physics that govern every token it predicts. When you send a prompt into a generative model, the system does not pause to reflect, nor does it possess an internal reservoir of beliefs, intentions, or awareness. Instead, it transforms your words into numerical vectors, projects those vectors into an immense geometric space, and calculates the trajectory of highest statistical plausibility. Every sentence it produces is the result of trillions of mathematical operations designed to balance coherence, relevance, and semantic depth. If you do not understand how this vector space operates, you will inevitably fall victim to common pitfalls such as hallucinations, prompt fragility, context degradation, and unpredictable system failures. Consider the paradox at the heart of modern artificial intelligence. We have built software systems capable of writing complex code, analyzing intricate legal contracts, synthesizing scientific literature, and composing nuanced prose. Yet these systems cannot perform multi-digit arithmetic with absolute certainty unless we explicitly connect them to an external calculator. They can mimic the style of a world-class philosopher while simultaneously fabricating a non-existent court case with absolute linguistic confidence. To harness the immense power of generative artificial intelligence while avoiding its catastrophic failure modes, you must develop an uncompromising, system-level mental model of how these architectures function from the ground up. Throughout this masterclass, we will deconstruct the entire landscape of generative artificial intelligence, moving systematically from core physical mechanisms to high-level enterprise architectures. We will examine the precise boundary separating artificial intelligence, machine learning, deep learning, and generative models. We will explore how large language models are constructed, how their self-attention mechanisms evaluate relationships across vast sequences of text, and why token prediction creates both astonishing capabilities and unavoidable vulnerabilities. We will then transition from theoretical foundations into practical execution, breaking down the exact mechanics of high-performance prompt engineering. You will learn why context is often far more influential than the prompt itself, how to manage the finite boundaries of context windows without losing critical information, and how to adapt your approach across major foundation models. We will examine rigorous verification workflows, explore the ethical and security trade-offs of deploying autonomous systems, and trace the evolutionary path from standalone conversational prompts to deterministic multi-step pipelines and autonomous agentic loops. Finally, we will navigate the official educational ecosystems and industry certifications offered by leading artificial intelligence organizations, providing you with a clear roadmap to validate and advance your expertise. Whether you are designing enterprise software architectures, automating complex analytical workflows, or seeking a rigorous conceptual understanding of the technology reshaping the global economy, this masterclass will serve as your comprehensive blueprint. By approaching this subject with the mindset of a systems architect, you will learn to look past the surface-level magic of generative text and see the underlying data flows, probability distributions, and operational constraints that govern modern machine intelligence. Let us begin by breaking down the core foundations that define generative artificial intelligence. To build a solid engineering foundation, we must first establish clear conceptual boundaries around the terms artificial intelligence, machine learning, deep learning, and generative artificial intelligence. These terms are frequently conflated in popular discourse, but in software architecture and computer science, they represent distinct, nested layers of abstraction. Imagine a set of concentric spheres. The outermost sphere encompasses the entire discipline of artificial intelligence. At its broadest definition, artificial intelligence refers to any computational system designed to perform tasks that traditionally require human cognitive capabilities. This includes symbolic logic, expert systems, rule-based inference engines, search algorithms, and planning systems. An expert system consisting of thousands of handcrafted conditional rules that diagnoses engine failures is a form of artificial intelligence. Even though it contains no statistical learning, no neural networks, and no capacity to adapt beyond its hard-coded logic. Nested directly inside artificial intelligence is machine learning. Machine learning represents a fundamental paradigm shift in how software operates. In traditional software development, human engineers write explicit deterministic rules that transform input data into expected outputs. If you want to detect spam emails using traditional programming, you write functions that search for specific keywords, analyze sender domains, and tally predefined red flags. In machine learning, this dynamic is inverted. Instead of programming the rules manually, you feed the system large volumes of historical input data alongside corresponding labels or outcomes. The machine learning algorithm analyzes the statistical patterns within that data and derives the mathematical rules automatically. Within machine learning, another nested sphere represents deep learning. Deep learning relies on artificial neural networks structured in multiple interconnected layers. Inspired loosely by the biological architecture of neurons in the human cortex, these networks process data through successive layers of mathematical transformations. Each layer extracts progressively higher levels of abstraction. When processing an image, the initial layers might detect simple edges and gradients. Intermediate layers combine those edges to identify textures and geometric shapes, and deep layers recognize complex objects like human faces or vehicles. Deep learning removed the need for manual feature engineering, allowing algorithms to discover subtle, nonlinear relationships across millions of data points simultaneously. Generative artificial intelligence sits at the core of these nested domains as a specialized application of deep learning. Historically, most machine learning systems were discriminative. A discriminative model calculates conditional probabilities to classify, score, or categorize existing data. It takes an input, such as an audio recording or a medical scan, and determines whether it represents a specific command or an abnormality. Discriminative models map inputs to discrete labels or continuous numerical values, essentially drawing mathematical decision boundaries that separate different classes of data in high-dimensional space. Generative models, by contrast, learn the underlying probability distribution of the data itself. Instead of merely distinguishing between different classes of information, a generative model learns how the data is constructed so that it can sample from that distribution to synthesize entirely new instances that never existed before. When trained on a vast corpus of literature, a generative language model does not simply categorize sentences. It models the statistical likelihood of how words, phrases, and concepts assemble, allowing it to generate novel, coherent paragraphs on demand. To understand how a generative model accomplishes this, we must examine the architecture of a large language model from its foundational input pipeline to its highest level of abstraction. At its core, a large language model is a deep neural network trained on vast quantities of text to model the statistical structure of human language. However, a computer cannot process raw text directly. Computers can only perform mathematical operations on numbers. Therefore, the first step in the pipeline of any language model is tokenization. Tokenization is the process of breaking down raw text into discrete mathematical units called tokens. A token is not necessarily an entire word. Depending on the tokenization algorithm, such as byte pair encoding, word piece, or sentence piece, a token can represent a single character, a subword fragment, a syllable, punctuation, or a common complete word. For example, common English words like computer or network might each be assigned a single token, whereas rare terminology, compound words, or lines of code might be split into several subword tokens. To visualize how byte pair encoding works, imagine starting with a vocabulary that contains only individual characters and symbols. The algorithm scans a massive training corpus and counts the frequency of every adjacent pair of characters. It identifies the most frequently occurring pair, such as the letters T and H, merges them into a single new subword token TH, and adds it to the vocabulary. The algorithm repeats this merging process hundreds of thousands of times. Frequent words like the or common conjunctions like and quickly become single tokens, while rare words are constructed by combining smaller subword fragments. This subword approach solves a major engineering dilemma, the out-of-vocabulary problem. In older natural language systems that operated on whole words, encountering an unfamiliar word or a typographical error caused the system to fail because the word was not present in its fixed dictionary. By breaking words into subwords and falling back to individual byte-level characters when necessary, modern tokenizers can process any arbitrary string of text, including code, mathematical formulas, foreign scripts, and invented terminology, without ever encountering an unparsable input. However, tokenization introduces important operational trade-offs. The composition of the tokenizer vocabulary directly impacts the computational efficiency and cost of processing different languages. Because most foundation models are trained on corpora dominated by English text, the tokenizer vocabulary contains thousands of dedicated tokens for complete English words and common phrases. In low-resource languages or languages with non-Latin scripts, words are frequently fractured into numerous single-character or multi-byte tokens. Consequently, a paragraph written in a low-resource language may require 3 to 4 times as many tokens to express the same semantic concept as an equivalent paragraph in English. Because model inference costs and context window consumption scale directly with token counts, this architectural asymmetry creates significant cost and latency disparities across different languages. Furthermore, tokenization affects numerical and code reasoning. If a tokenizer splits a multi-digit number into arbitrary 2-digit and 3-digit chunks, the neural network must learn arithmetic across fragmented numerical tokens rather than unified mathematical digits. Modern architectures design specialized tokenizers that enforce single-digit tokenization for numbers and preserve indentation whitespace for programming code, substantially boosting mathematical and syntactic precision. Each unique token in the model vocabulary is assigned a specific integer identification number. When you input a phrase into a model, the tokenizer converts that sequence of characters into a sequence of integers. If a model has a vocabulary of 100,000 tokens, Every piece of written text in any supported language is represented as a sequence drawn from this fixed vocabulary. Once text is converted into integers, the model projects each token into a high-dimensional continuous geometric space known as an embedding space. An embedding is a dense vector, an array of floating point numbers, that represents the semantic and grammatical properties of a token. In modern foundation models, these vectors typically possess thousands of dimensions, such as 4096 or 8192 continuous numerical coordinates. Visualize this embedding space as an immense room with thousands of geometric axes. In this space, tokens with similar meanings, syntactic functions, or conceptual relationships are positioned close to one another. The vector representing the word ocean will be situated near the vector for sea, water, and wave, while remaining distant from the vector representing microchip. Furthermore, the directional relationships between vectors capture abstract conceptual relationships. The mathematical vector pointing from king to queen is nearly identical in direction and magnitude to the vector pointing from man to woman, capturing the abstract concept of gender across different societal roles. Similarly, the vector connecting a country to its capital city exhibits consistent geometric alignment across different geographic entities. To measure relationships within this space, algorithms calculate geometric distance metrics. The most common metric is cosine similarity, which measures the cosine of the angle between two multidimensional vectors. If two vectors point in the exact same direction, their cosine similarity is 1, indicating identical semantic orientation regardless of vector magnitude. If they are orthogonal, their similarity is 0, indicating no semantic correlation. Another metric is Euclidean distance, which measures the straight-line physical distance between vector coordinates, and dot product similarity, which combines both directional alignment and vector magnitude. However, language is sequential, and the meaning of a word depends not only on its presence, but on its exact position within a sentence. The sentence "the dog chased the cat" conveys the exact opposite meaning of the sentence "the cat chased the dog," even though both sentences contain the exact same set of word tokens. Because the transformer architecture processes all tokens in a sequence simultaneously rather than sequentially, it possesses no native awareness of word order. To provide this positional awareness, the model injects positional encodings into the token embeddings. In early transformer architectures, positional encodings were static sinusoidal waves added directly to the input vectors. In modern foundation models, architectures utilize advanced dynamic positional methods such as rotary position embeddings, commonly known as rope, or attention with linear biases known as alibi. Rotary position embeddings incorporate positional information by mathematically rotating the query and key vectors in the complex plane based on their relative distance from one another. This allows the model self-attention mechanism to recognize not only where a word appears in absolute terms, but precisely how far apart two words are relative to each other, improving the model ability to generalize across long documents and maintain grammatical coherence over thousands of tokens. Furthermore, rope enables context window scaling through positional interpolation techniques like yarn. By mathematically compressing the rotation angles across extended token distances, engineers can expand a model context window from 8,000 tokens to over 100,000 tokens without requiring massive retraining from scratch. With positional embeddings established, we can now examine the core engine of generative artificial intelligence, the transformer neural network architecture. To appreciate why the transformer revolutionized artificial intelligence, we must understand the sequence modeling architectures that preceded it, such as recurrent neural networks and long short-term memory networks. In a recurrent network, the model processed text sequentially, one word after another, similar to reading a tape from left to right. As it read each word, it updated an internal hidden state vector intended to carry forward the memory of everything it had seen so far. This sequential processing created two fatal engineering bottlenecks. First, it made it impossible to parallelize training across large clusters of graphics processing units. Because Step 10 could not be calculated until Step 9 was completed, training massive models on billions of words was computationally intractable. Second, recurrent models suffered from catastrophic forgetting and vanishing gradients over long sequences. As the sequence grew to hundreds or thousands of words, the mathematical memory of early sentences became diluted and overwritten by intermediate words, causing the model to lose track of dependencies over long distances. The transformer architecture eliminated recurrent loops entirely, replacing them with the self-attention mechanism. The self-attention mechanism processes all tokens in a sequence simultaneously, allowing every token to examine, compare itself against, and dynamically absorb contextual information from every other token in the sequence in a single parallel operation. To understand how self-attention functions mathematically and conceptually, visualize a research library where every token in a sequence acts as an investigator holding three distinct items: a query, a key, and a value. Each of these items is a mathematical vector derived by multiplying the token embedding by learned weight matrices. The query vector represents what the token is actively searching for to clarify its own meaning or resolve grammatical relationships. The key vector represents a label describing what semantic and syntactic information the token contains. The value vector represents the actual content or meaning that the token can contribute to others. When calculating attention for a specific token, the model takes that token query vector and calculates a mathematical dot product against the key vectors of all tokens in the entire sequence, including itself. The dot product measures how closely the query matches each key in the geometric vector space. If the query of the word bank matches the key of the word river, the dot product produces a high numerical score. If it matches the key of an unrelated word, the score is low. To prevent the dot product scores from becoming excessively large in high-dimensional spaces, which would cause mathematical gradients to vanish during training, the raw scores are divided by the square root of the dimension of the key vectors. This scaling factor stabilizes the mathematical gradients. The scaled scores are then passed through a softmax mathematical function. The softmax function converts the scores into a normalized probability distribution where all attention weights sum to exactly 1. These weights act as a dynamic spotlight, determining how much focus the model should place on each word in the sequence. Finally, the model multiplies these normalized attention weights by the corresponding value vectors of each token and sums them together. The result is a context-enriched vector representation that blends the original meaning of the word with the specific context provided by the surrounding sentence. The word bank is no longer just an isolated token. Its internal vector has absorbed the fluid, environmental context of the surrounding words river and water. In generative language models, which generate text autoregressively from left to right, the self-attention mechanism is subject to a strict causal masking constraint. When the model is predicting the fifth word in a sentence, it must not be allowed to look ahead at words 6, 7, or 8. To enforce this, the architecture applies an upper triangular causal attention mask. This mask mathematically sets the attention scores between any token and all subsequent future tokens to negative infinity. When passed through the softmax function, negative infinity becomes 0, ensuring that a token can only attend to preceding tokens and itself, preserving the integrity of the autoregressive prediction process. In contrast to causal self-attention, encoder-decoder models implement cross-attention. In cross-attention, the query vectors come from the generated target sequence, while the key and value vectors come from the encoded source sequence. Cross-attention allows models to bridge two distinct modalities or languages, making it the preferred architecture for machine translation, audio transcription, and image captioning. To capture multiple types of relationships simultaneously, modern architectures implement multi-head self-attention. Instead of running a single attention calculation, the architecture splits the query, key, and value vectors across multiple parallel heads, typically 32, 64, or more heads per layer. One attention head might specialize in tracking grammatical syntax and subject-verb agreements. Another head might focus on resolving pronoun references, such as determining what the word it refers to in a complex sentence, while a third head tracks overarching thematic concepts. The outputs of all these attention heads are concatenated and projected through a feed-forward neural network layer. To optimize memory and compute during inference, modern architectures have evolved beyond standard multi-head attention to multi-query attention and grouped query attention. In standard multi-head attention, every single attention head maintains its own independent key and value heads. While highly expressive, this creates massive memory overhead when storing the key-value cache in GPU memory during long context generation. Multi-query attention drastically simplifies this by having all query heads share a single key head and a single value head. This compresses the key-value cache memory footprint by up to 90%, though it can slightly reduce model nuance on complex reasoning tasks. Grouped query attention achieves an ideal balance. It partitions query heads into small groups, such as 8 groups of 4 heads, where each group shares a single key and value head. Grouped query attention preserves virtually all the expressive power of multi-head attention, while drastically reducing GPU memory consumption and enabling blistering inference speeds on massive sequence lengths. To achieve even greater efficiency in large-scale deployments, modern architectures implement multi-head latent attention. Multi-head latent attention compresses both the key and value projections into a low-dimensional latent vector before storing them in the key-value cache. During generation, the attention heads decompress these latent vectors on the fly. This breakthrough allows the model to maintain the full expressive power of standard multi-head attention while reducing KV cache memory consumption to a fraction of traditional grouped query attention. Furthermore, during large-scale model training, engineers utilize activation checkpointing, also known as gradient checkpointing. In standard backpropagation, the intermediate activation tensors of every transformer layer must be held in graphics memory throughout the forward pass so they can be used to calculate gradients during the backward pass. For deep models with dozens of layers, this consumes massive amounts of GPU memory. Activation checkpointing saves memory by retaining activations only at the boundaries of transformer blocks, discarding intermediate layer activations. During the backward pass, the system recomputes the intermediate activations on the fly within each block. By trading a modest 20% increase in computation time, activation checkpointing slashes memory consumption by up to 70%, enabling the training of substantially larger models on existing hardware clusters. A single transformer block consists of 2 primary components: the multi-head self-attention layer, and the feed-forward network, also known as the multi-layer perceptron. The feed-forward network consists of fully connected linear layers separated by nonlinear activation functions. While older neural networks utilize simple rectified linear units, modern foundation models employ advanced gated activation functions such as SWI-GLU or Gaussian error linear units. SWI-GLU operates by splitting the hidden representation into two parallel linear projections, applying a swish nonlinear activation to one branch and multiplying it element-wise with the other branch before projecting back to the hidden dimension. This gating mechanism acts like a dynamic filter, allowing the model to regulate the flow of factual information and abstract reasoning patterns through its layers without suffering from dead neuron saturation. Furthermore, leading foundation architectures frequently utilize the mixture of experts architecture. In a mixture of experts model, the standard dense feed-forward layer is replaced with multiple parallel expert subnetworks, such as 8 or 16 distinct expert networks per layer. A lightweight router network dynamically calculates routing probabilities for each incoming token, dispatching the token to only the top two most relevant expert networks. While the total model contains hundreds of billions of parameters across all experts, only a fraction of those parameters are active for any given token forward pass. This achieves the vast knowledge capacity of an immense foundation model while maintaining the low compute cost and low latency of a much smaller dense model. Throughout this deep architecture, residual connections and layer normalization, such as RMS norm, are applied before and after every block. RMS norm normalizes token activation vectors based on their root mean square, ensuring that mathematical signals remain numerically stable without requiring costly mean centering operations. Residual connections allow raw mathematical signals to bypass intermediate layers, preventing the vanishing gradient problem during training and ensuring that low-level semantic details are preserved alongside high-level abstract reasoning. Modern foundation models stack dozens or even hundreds of these transformer blocks on top of one another, scaling from billions to hundreds of billions of trainable parameters. To understand how a raw neural network becomes a practical assistant, we must look at the distinct phases of model development: pre-training, supervised fine-tuning, and preference alignment. Pre-training is the most computationally demanding phase. During pre-training, the model is fed trillions of tokens of text scraped from the public internet, books, code repositories, and academic papers. Its sole objective is causal language modeling. Given a sequence of tokens, predict the next token. By minimizing its prediction error across trillions of words, the model internalizes grammar, factual knowledge, coding logic, and broad world patterns. The compute required for pre-training is governed by scaling laws, such as the chinchilla scaling laws, which establish that for optimal performance, model parameter size and training token volume should scale in equal proportion. Training a 70 billion parameter model requires at least 1.4 trillion high-quality tokens to achieve compute optimal efficiency, proving that data quality and token volume are just as vital as raw parameter count. However, a pre-trained base model is merely a text completion engine. If you ask a base model, how do I configure a database, it might not answer the question. It might simply generate a list of related exam questions because that pattern frequently followed that phrase in its training data. To transform a base model into a helpful conversational assistant, developers perform supervised fine-tuning. In this phase, the model is trained on curated datasets of high-quality demonstration conversations, where human experts demonstrate ideal answers to complex instructions. This aligns the model to recognize instruction following patterns. When organizations wish to customize a model for specialized enterprise domains without the immense cost of full parameter fine-tuning, they employ parameter-efficient fine-tuning techniques like low-rank adaptation, commonly known as LoRA. LoRA freezes the pre-trained model weights and injects small, trainable rank decomposition matrices into the self-attention and feed-forward layers. Instead of updating billions of parameters, LoRA updates only a few million parameters, reducing fine-tuning memory requirements by over 80% while achieving comparable performance. When combined with 4-bit quantization in QLoRA, teams can fine-tune state-of-the-art foundation models on a single consumer graphics card. Following supervised fine-tuning, the model undergoes preference optimization using techniques like reinforcement learning from human feedback, direct preference optimization, or Kahneman-Tversky optimization. These techniques train the model to prioritize helpful, safe, and factually rigorous answers over unhelpful, toxic, or fabricated responses. Additionally, we must consider the hardware and compute realities of running these models. Running a model containing hundreds of billions of parameters requires substantial graphics processing unit memory. Modern high-performance compute clusters utilize specialized floating-point formats, such as float16. Float16 allocates 8 bits to the exponent and 7 bits to the mantissa, matching the dynamic numerical range of full 32-bit floating-point numbers while cutting memory bandwidth in half and preventing mathematical underflow or overflow during massive parallel gradient updates. Furthermore, hardware-level memory management is optimized through flash attention. In standard attention, the intermediate attention matrices are repeatedly read from and written to high-bandwidth graphics memory, creating severe memory latency bottlenecks. Flash attention tiles the computation into small blocks that fit directly within high-speed on-chip SRAM memory, computing softmax normalization incrementally without materializing the full attention matrix in main memory. This transforms the input-output memory complexity of attention from quadratic to linear, enabling unprecedented generation speeds across massive context windows. To handle infinite sequence streaming without running out of GPU memory, modern systems employ attention sink eviction algorithms, such as streaming LLM. Researchers discovered that language models allocate massive attention weights to the very first few tokens in a sequence, acting as attention sinks that anchor the attention distribution. By preserving these initial attention sink tokens alongside a sliding window of the most recent tokens, streaming LLM allows models to generate millions of tokens continuously without performance collapse or memory overflow. To accelerate generation throughput further, inference engines utilize speculative decoding. Speculative decoding pairs a massive, high-accuracy target foundation model with a lightweight, high-speed draft model. The small draft model speculatively predicts 5 or 6 candidate tokens ahead at extreme speed. The large target model then evaluates all speculative tokens simultaneously in a single parallel forward pass, accepting valid tokens and regenerating from the point of any divergence. Because verifying tokens in parallel requires the same compute as generating a single token, speculative decoding accelerates inference speeds by 2 to 3 times without altering the mathematical probability distribution of the output. To reduce memory consumption and accelerate inference speeds further, engineers utilize quantization. In standard training, model weights are represented as 16-bit or 32-bit floating point numbers. Quantization compresses these weights into 8-bit or 4-bit integers using advanced techniques like AWQ or GPTQ. While aggressive quantization can introduce minor degradation in nuanced reasoning, Modern 4-bit and 8-bit quantization schemes allow massive models to run on significantly smaller hardware footprints with minimal loss of accuracy. Now that we understand how the transformer is built and trained, we can explore how these models actually generate text during inference. The vast majority of modern generative language models are autoregressive decoder-only transformers. When you submit a prompt, the model processes the entire input sequence through its layers of self-attention and feed-forward networks. At the final output layer, the model does not produce a finished sentence or an immediate answer. Instead, it outputs a vector of raw numerical scores called logits for every single token in its vocabulary. If the vocabulary contains 100,000 possible tokens, the model outputs 100,000 logits. Each logit represents the unnormalized statistical score indicating how likely that specific token is to be the correct continuation of the sequence. To understand the mathematical implementation of softmax within high-performance GPU kernels, we must examine numerical stability techniques. In raw mathematical computation, calculating the exponential of large positive logit values can quickly exceed the maximum representation limit of 16-bit floating-point registers, causing arithmetic overflow. To prevent overflow, hardware implementations apply the log-sum-exp numerical stabilization trick. Before exponentiating logits, the kernel identifies the maximum logit value across the vocabulary and subtracts that maximum value from all logits in the vector. Because subtracting a constant shift does not alter the resulting softmax probability distribution, this guarantees that all exponentiated values remain between 0 and 1, ensuring mathematical stability across billions of parallel operations. Furthermore, dynamic context extension through yarn operates by treating high-frequency and low-frequency components of rotary position embeddings differently. High-frequency dimensions represent local, fine-grained grammatical syntax, while low-frequency dimensions capture long-range semantic dependencies spanning thousands of words. Yarn applies progressive interpolation to low-frequency dimensions while preserving the exact rotation angles of high-frequency dimensions, allowing language models to extend their operational context window across hundreds of thousands of tokens without losing grammatical precision. To turn these raw logits into usable probabilities, the model passes them through a softmax mathematical function. This converts the logits into a probability distribution where every candidate token is assigned a percentage chance of appearing next, and the sum of all percentages equals 100%. At this stage, the decoding strategy determines how the model selects the next token from this probability distribution. The simplest approach is greedy decoding, where the system always chooses the single token with the absolute highest probability. While greedy decoding is computationally straightforward, it often leads to repetitive, generic, and unnatural text because human language does not always follow the single most probable statistical path. To introduce natural variation, creativity, and nuance, engineers use stochastic sampling techniques controlled by hyperparameters such as temperature, top K, and top P sampling. Temperature is a mathematical parameter that scales the raw logits before they pass through the softmax function. When you set the temperature to a low value, such as 0.2, the mathematical differences between logits are amplified. The highest probability tokens become overwhelmingly dominant, while less probable tokens are suppressed toward 0. This results in highly deterministic, conservative, and focused output, which is ideal for structured data extraction, technical documentation, and mathematical reasoning. Conversely, when you raise the temperature to a high value, such as 0.9 or 1.2, the distribution is flattened. The differences between high-scoring and medium-scoring tokens shrink, giving less obvious tokens a higher statistical chance of being selected. This produces more diverse, unexpected, and creative language, though setting the temperature too high introduces chaotic phrasing and incoherent logic. To prevent the model from selecting completely bizarre or irrelevant tokens when using high temperatures, engineers combine temperature with top K and top P sampling. Top K sampling sets a hard numerical limit on the candidate pool. If K is set to 40, the model sorts all vocabulary tokens by their probability score and discards everything outside the top 40 candidates. The model then renormalizes the probabilities across those 40 tokens and samples from that restricted subset. Top P sampling, also known as nucleus sampling, takes a dynamic approach based on cumulative probability. Instead of selecting a fixed number of tokens, Top P sets a cumulative probability threshold, such as 0.9. The model sorts candidate tokens from highest to lowest probability and includes tokens in the selection pool until their combined probabilities equal 90%. If the model is highly confident about the next word, the nucleus might contain only 2 or 3 tokens. If the context is open-ended and ambiguous, the nucleus expands dynamically to include dozens of plausible words. Another modern sampling technique is min-P sampling. Min-P sets a minimum probability threshold relative to the highest probability token. If the top candidate has a 60% probability and min-P is set to 0.05, the model discards any token whose probability is less than 5% of that top token, effectively scaling the candidate pool based on the model confidence without requiring arbitrary fixed counts. Additionally, sampling can be constrained by repetition penalties, frequency penalties, and presence penalties. A presence penalty applies a mathematical deduction to the logits of any token that has already appeared in the generated text, encouraging the model to introduce new topics. A frequency penalty scales the deduction based on how many times a token has appeared, actively discouraging repetitive loops and monotonous phrasing. Once the decoding strategy selects a single token, that new token is appended to the end of the input sequence. The expanded sequence is then fed back into the transformer, and the entire cycle repeats to predict the subsequent token. This continuous loop continues until the model generates a special designated end-of-sequence token or reaches a predefined maximum token limit. Understanding this token-by-token autoregressive mechanism reveals the true nature of how large language models function. The model does not formulate an entire thought, outline a logical argument, and then translate that idea into words. It operates through continuous local statistical prediction shaped by the global context of the preceding tokens. This leads us to an essential evaluation of the real strengths and fundamental limitations of generative artificial intelligence. The greatest strength of large language models lies in their ability to perform high-dimensional pattern recognition, semantic transformation, and cross-domain synthesis. Because they have mapped the statistical structure of billions of texts, they excel at translating information between different formats, summarizing complex technical reports, extracting structured entities from unstructured prose, adjusting the tone and register of communication, and identifying analogous concepts across disparate disciplines. Furthermore, language models serve as versatile reasoning engines when prompted correctly. While they do not possess conscious reasoning, the mathematical transformations within their deep layers capture the logical structures embedded in human discourse. When guided through explicit step-by-step progressions, they can decompose intricate engineering problems, generate functional code across numerous programming languages, and assist in rigorous hypothesis generation. However, the architecture imposes critical engineering limitations that must never be overlooked. First, language models possess no persistent, real-time awareness of the physical world. Their internal weights are frozen after the pre-training and fine-tuning phases are completed. Unless augmented with external search mechanisms or retrieval tools, a model has no knowledge of events, discoveries, or data changes that occurred after its training cutoff. Second, language models lack a native, formal execution engine for symbolic logic and mathematics. Because they operate through statistical token association rather than deterministic computation, they can struggle with multi-digit multiplication, complex symbolic algebra, or precise logic puzzles if forced to generate the answer directly in a single token jump. They do not calculate numbers. They predict what a calculation looks like based on patterns in their training data. Third, language models have no internal mechanism to verify their own claims against objective reality. A model does not feel doubt or uncertainty in the way a human does. When a model outputs text, every token is simply the result of a probability distribution. It will output a completely fabricated statement with the exact same linguistic fluency, authoritative tone, and syntactic precision as an empirically verified scientific fact. This phenomenon is known as hallucination, and understanding why it occurs is essential for any engineer working with artificial intelligence. A hallucination occurs when a generative model produces assertions that are factually incorrect, logically inconsistent, or entirely fabricated, despite appearing plausible and coherent. To understand why hallucinations happen, we must look at the mathematical objective function used during model training. Large language models are trained to minimize prediction error on training text. In mathematical terms, they are optimized for statistical plausibility, not absolute empirical truth. The model learns to generate sequences that sound like high-quality human language. When a model encounters a prompt regarding a well-documented subject with millions of consistent references in its training data, the vector paths in its attention layers converge strongly toward historically accurate tokens. However, when you query the model about a highly specific, niche, or obscure topic where training data is sparse, or when you ask it to connect two unrelated concepts, the statistical probability landscape becomes flat and ambiguous. In this flat probability space, several different candidate tokens have similar statistical likelihoods. The model cannot stop and say to itself that it lacks sufficient data to answer unless it has been explicitly aligned to recognize epistemic uncertainty. Instead, the autoregressive engine continues sampling tokens based on grammatical rules and stylistic associations. As soon as the model generates the first fabricated token, that token becomes part of the permanent context for all subsequent predictions. The self-attention mechanism now attends to its own fabricated output, treating it as established ground truth. This causes the model to double down on the fabrication, generating supporting citations, fictional historical dates, or imaginary API parameters to maintain contextual consistency with the error it just introduced. Another primary driver of hallucinations is sycophancy, where the model prioritizes agreeing with the premise of the user prompt over stating objective reality. If a user asks a leading question, such as why an imaginary historical event occurred, the attention mechanism is heavily primed by the concepts in the user question. The model will often generate a detailed, fictional explanation justifying the false premise rather than correcting the user misconception. Mitigating hallucinations requires a disciplined engineering approach. We cannot eliminate the probabilistic nature of neural networks, but we can constrain their operational environment. By providing grounded reference documents through retrieval-augmented generation, enforcing structured schema outputs, using low-temperature settings for deterministic tasks, and structuring prompts to encourage explicit verification steps, we can significantly reduce the frequency and severity of model fabrications. With these core architectural mechanics and limitations clearly established, we can now turn our attention to the primary interface through which we control these statistical systems, the discipline of effective prompting. Prompting is often described as the art of communicating with an artificial intelligence, but in software engineering, it is more accurately understood as the deterministic steering of a high-dimensional probabilistic system. When you write a prompt, you are not engaging in casual dialogue. You are supplying the initial boundary conditions that collapse trillions of potential token trajectories into a specific, predictable output path. To master this discipline, we must dissect the anatomy of an effective prompt. A robust, production-grade prompt consists of 6 core architectural components: the persona or role definition, the primary objective, the operational context, the input data, the structural constraints, and the negative constraints. The persona or role definition establishes the baseline perspective, expertise level, and tone of the model. By declaring that the system should operate as a principal systems architect, an expert security auditor, or a senior technical writer, you immediately shift the attention weights towards specific clusters of specialized vocabulary, reasoning frameworks, and conceptual paradigms within the embedding space. This restricts the model from generating generic, superficial generalizations and primes it for professional depth. The primary objective is the explicit, unambiguous statement of what the model must accomplish. This must be phrased using direct action verbs such as analyze, synthesize, extract, translate, refactor, or evaluate. Ambiguity in the primary objective introduces variance into the token sampling process, increasing the likelihood of unhelpful responses. The operational context provides the background information, business rules, target audience specifications, and situational parameters necessary for the model to make informed decisions. Without context, the model relies entirely on average statistical patterns found in its training corpus, which may not align with your specific domain requirements. The input data represents the raw material the model must process. This could be a block of unstructured text, a configuration file, customer feedback transcripts, or a set of technical requirements. High-performance prompts clearly demarcate where the instructions end and where the input data begins using structural delimiters such as quotation marks, triple backticks, or designated tag blocks. The structural constraints define the exact formatting, length, and organizational schema of the expected response. Rather than allowing the model to choose its own output structure, you specify whether it should respond in raw JSON conforming to a specific schema, a concise 3-paragraph summary, a comparative analysis table, or a series of numbered engineering recommendations. Finally, negative constraints explicitly identify what the model must avoid. This includes prohibiting unnecessary introductory fluff, forbidding speculative claims when data is missing, restricting the use of specific terminology, or preventing the inclusion of conversational filler like certainly or here is your answer. The foundation of every high-performance prompt is the combination of clarity, specificity, and operational context. A common misconception among beginners is that artificial intelligence possesses intuition. If you provide a vague prompt such as "make this report better," the model has no way of knowing whether better means more concise for an executive, more technically granular for an engineering team, or more persuasive for a client. To achieve precision, you must eliminate qualitative adjectives and replace them with quantitative metrics and operational criteria. Instead of asking for a brief summary, specify that the response must be between 150 and 200 words, structured into exactly 2 paragraphs, focusing exclusively on operational cost trade-offs. By replacing open-ended adjectives with concrete constraints, you drastically reduce the statistical entropy of the token distribution, steering the model toward a predictable and repeatable outcome. To understand the difference between amateur and professional prompt engineering, consider a concrete scenario. Suppose an engineer wants a model to evaluate an API architecture. An amateur prompt reads, "Review this API and tell me if it is good and how to improve it." This prompt fails across every dimension. It lacks a defined persona, provides no context on scale or traffic patterns, establishes no evaluation criteria, and leaves the output structure completely unconstrained. The model will produce a generic, superficial list of basic suggestions. In contrast, a professional, production-grade prompt begins by defining the persona as a senior cloud infrastructure engineer. It specifies the operational context: a microservices architecture handling 50,000 requests per second with strict sub-50 millisecond latency requirements. It provides the API endpoint definitions wrapped within clear structural delimiters. It sets the primary objective: conduct a performance and resilience audit focusing on database query bottlenecks, rate limiting, and failure cascading. It defines the structural constraints. Output the findings in a structured format containing the identified vulnerability, the technical root cause, and the refactored design pattern. Finally, it enforces negative constraints. Do not include generic introductory text, do not comment on naming conventions, and focus exclusively on high concurrency throughput risks. When the foundation model evaluates this second prompt, its attention heads are locked onto high concurrency distributed systems principles, resulting in an authoritative, deeply technical analysis that directly addresses the engineering reality. Across all foundation models, several universal prompting techniques have emerged as essential engineering tools. The first of these is the strategic separation between system messages and user messages. In modern generative architectures, conversational interactions are structured into distinct message channels or roles. The system message, sometimes called the developer instruction or system instruction, operates at a higher level of authority than standard user messages. It is designed to establish permanent guardrails, persistent personas, formatting rules, and core behavioral policies that remain active throughout an entire multi-turn interaction. When an instruction is placed in the system channel, the model weights treat it as a foundational constraint that applies across all subsequent turns. In contrast, the user channel represents the dynamic, turn-by-turn inputs submitted by the operator. Placing your overarching formatting schemas and negative constraints in the system message ensures that they are not diluted or overridden as the conversation grows in length. To protect system instructions against user manipulation or malicious injection within untrusted data payloads, production prompts implement the sandwich defense. In a sandwich defense architecture, core operational constraints and formatting schemas are injected twice. First in the initial system message at the top of the prompt payload, and again as an instructional anchor at the very bottom of the user message following the untrusted input data. This ensures that the model attention heads attend to the strict constraints right before token generation begins, neutralizing adversarial attempts to override instructions located inside the body data. The second universal technique is explicit output schema enforcement. Language models are inherently verbose because their training data contains conversational pleasantries and introductory phrases. In automated workflows or data processing pipelines, conversational filler breaks downstream parsers and degrades system reliability. To eliminate this variability, you must instruct the model to output purely structured data without conversational framing. You can define a strict JSON schema, specifying exact key names, data types, and required fields, accompanied by an explicit instruction to return only valid JSON and nothing else. In advanced production architectures, schema enforcement is achieved through context-free grammar logit masking engines. Instead of relying purely on the model adherence to text instructions, grammar-guided generation engines, such as outlines or guidance, intercept the raw logits before token sampling occurs at every step. If the JSON schema requires a closing bracket or an integer value at a specific token position, the grammar engine mathematically sets the logits of all invalid tokens to negative infinity. This physically prevents the neural network from generating malformed syntax, guaranteeing 100% compliance with the defined schema. Additionally, developers can utilize logit bias steering. Logit bias allows an engineer to manually inject a positive or negative mathematical offset to specific token identification numbers in the vocabulary. If you want to strictly prevent a model from generating the word Boolean or true in a specific context, you can apply a strong negative logit bias of -100 to those specific token integers, rendering them statistically impossible to sample during generation. The third foundational technique is few-shot conditioning, often referred to as in-context learning. While a zero-shot prompt provides only instructions without examples, a few-shot prompt includes several concrete input-output demonstration pairs directly within the context window. Few-shot prompting is one of the most reliable methods for aligning model output with complex formatting requirements and nuanced reasoning styles. When the self-attention mechanism processes input-output pairs, it computes the statistical mapping between the provided inputs and outputs. This allows the model to mirror your exact structural cadence, tone, classification schema, and edge case handling without requiring fine-tuning or weight modification. To implement few-shot conditioning effectively, provide between 2 and 5 high-quality, representative examples. Ensure that your examples cover diverse edge cases, such as handling missing data, ambiguous inputs, or malformed queries. If an input lacks necessary information, show an example where the model outputs an explicit error message or a structured placeholder rather than hallucinating an answer. Furthermore, dynamic few-shot selection can be implemented in automated pipelines. In a dynamic few-shot system, an embedding model evaluates incoming user queries, searches an indexed repository of hundreds of curated example pairs, and dynamically retrieves the 3 examples that are semantically closest to the current query. These relevant examples are injected into the prompt on the fly, providing the model with tailored demonstrations for the specific problem at hand. The fourth universal technique is step-by-step reasoning, formalized in artificial intelligence research as chain of thought prompting. To understand why chain of thought works, we must recall the autoregressive nature of transformer neural networks. A large language model has a fixed computational budget per token. During the forward pass that generates a single token, the model executes a fixed number of mathematical matrix multiplications across its layers. If you present a model with a complex logic puzzle, a multi-step mathematical problem, or an intricate architectural trade-off and immediately ask for the final answer, the model must compress all necessary reasoning into the generation of that single initial answer token. If the logic requires several intermediate deductive steps, the computational capacity of a single forward pass is often insufficient, resulting in an incorrect or superficial response. Chain of thought prompting resolves this limitation by instructing the model to think step by step and output its intermediate reasoning before arriving at a final conclusion. By generating tokens that describe each sequential deduction, the model externalizes its working memory into the context window. When predicting step 3 of a problem, the self-attention mechanism can look back at the tokens it generated during step 1 and step 2. This effectively scales the total computational budget of the task, because each intermediate token provides a new forward pass through the neural network, allowing the model to verify facts, cross-reference intermediate values, and maintain logical coherence throughout long deductive chains. Beyond basic chain of thought, advanced reasoning frameworks expand on this principle. One such framework is least-to-most prompting. In least-to-most prompting, the model first decomposes a complex problem into a sequence of simpler subproblems, and then solves them sequentially, passing the solved output of each subproblem into the context for the next. Another powerful framework is self-consistency sampling. In a self-consistency workflow, the system samples multiple diverse chain of thought reasoning paths from the model by running the prompt several times at a moderate temperature. The system then aggregates the final answers across all paths and selects the conclusion supported by the majority of the reasoning chains. This voting mechanism filters out random statistical errors and significantly improves accuracy on complex analytical tasks. A more expansive framework is tree of thoughts. In a tree of thoughts architecture, the model explores multiple branching reasoning paths simultaneously, evaluating intermediate thoughts, looking ahead to potential outcomes, and backtracking when a path leads to a logical dead end. This mirrors human strategic deliberation, making it effective for complex planning, architectural synthesis, and algorithmic optimization. Similarly, the graph of thoughts framework extends tree structures into arbitrary graphs, allowing intermediate reasoning branches from different paths to merge, synthesize, and cross-pollinate before arriving at a final solution. In modern programmatic artificial intelligence engineering, frameworks like DSP, short for Declarative Self-Improving Language Programs, represent a paradigm shift in how prompts are created. Instead of manually writing and hand-tuning fragile prompt strings, DSP treats language model pipelines as modular, compilable software programs. Engineers define high-level input and output signatures and specify an evaluation metric. A DSP teleprompter compiler then automatically searches the space of possible prompt instructions and few-shot exemplar combinations, testing candidates against a validation dataset. The compiler iteratively tunes the prompt parameters to maximize the metric score, producing robust, optimized prompts mathematically calibrated for specific foundation models. Beyond programmatic compilation, advanced practitioners utilize in-context metaprompting. Metaprompting involves instructing a foundation model to reflect on its own instructions, generating optimized system prompts, validation rules, and few-shot exemplars tailored for a specific subtask. This creates an automated prompt optimization loop where the model refines its own boundary conditions before executing downstream tasks. Furthermore, dynamic prompt composition architectures assemble complex prompts programmatically at runtime. Instead of relying on static text files, application frameworks utilize templating engines that dynamically pull system policies from database records, inject current runtime variables, bind verified domain tools, and append user queries within strict structural boundaries, preventing template injection and ensuring modular maintainability across large engineering teams. Furthermore, engineers must understand prompt fragility and token sensitivity. Because tokenization splits text based on frequency statistics, seemingly minor alterations in whitespace, casing, or punctuation can cause the tokenizer to split a word into completely different subword tokens. Changing a single character can shift the entire sequence of input token integers, altering the trajectory of the self-attention calculations and leading to unexpectedly divergent outputs. Rigorous prompt engineering requires testing prompts across diverse variations in formatting and casing to ensure operational stability. Despite the power of these techniques, developers and analysts frequently fall into common prompting traps that degrade performance. The first common mistake is over-reliance on negative constraints without providing positive directives. Human language and neural networks are both biased toward activation. When you repeatedly tell a model do not include marketing language, do not mention competitors, and do not use technical jargon, you fill the context window with the very concepts you wish to avoid, priming the attention heads with those semantic vectors. A far more effective strategy is to provide a positive directive that defines what the model should do instead, such as write in a neutral, objective, matter-of-fact tone using vocabulary accessible to a general business audience. The second common mistake is instruction dilution, where critical rules are buried within massive walls of unstructured text. When a prompt contains thousands of tokens of background documentation with important instructions scattered randomly throughout the body, the attention mechanism distributes its weights broadly, increasing the risk that specific constraints will be overlooked. To prevent instruction dilution, group all operational instructions into a dedicated section at the beginning or end of the prompt, using clear structural headings and delimiters. The third common mistake is assuming conversational state persistence across disconnected sessions. Language models are completely stateless. Every time an API request is made, the model evaluates only the tokens currently present within that specific payload. If you open a new session or clear the context, the model retains no residual memory of previous interactions. Expecting a model to remember earlier instructions without passing them explicitly in the payload leads to immediate task failure. The fourth common mistake is conversational drift. In long multi-turn interactions, as the conversation wanders across various topics, earlier constraints gradually recede into the middle of the expanding context window where attention weights decay. The model begins to forget its original formatting instructions or tone requirements. To prevent conversational drift, periodic summary prompts or clean session resets should be employed to re-anchor the model attention on core constraints. While universal principles apply across all generative systems, different foundation model platforms have distinct architectural optimizations and behavioral characteristics. Adapting your prompts to leverage the specific strengths of each major platform is a crucial skill for modern software engineers. When working with ChatGPT and OpenAI models, the system excels at strict instruction following, function calling, and structured schema generation. OpenAI models respond exceptionally well to developer and system messages that clearly outline operational policies. When defining complex data extraction tasks, leveraging OpenAI structured output mode ensures that the model mathematically constrains its token sampling to match a defined schema, guaranteeing that the generated output is valid and parsable by external applications. When working with Google Gemini models, the architecture is designed from the ground up for multimodal processing and expansive context windows. Gemini excels at ingesting massive documents, entire code bases, audio files, and high-resolution video streams simultaneously. When prompting Gemini, you can provide extensive source material and rely on its long context attention mechanisms to perform precise cross-document analysis. To maximize performance on Gemini, use clear system instructions to establish task parameters and provide structured reference documents, utilizing its multimodal capabilities by directly interleaving text instructions with visual or audio inputs. When working with Microsoft Copilot, the system operates as an enterprise orchestration layer embedded within workplace productivity environments and cloud platforms. Copilot prompts frequently interact with enterprise data retrieved via semantic search across emails, documents, and corporate databases. When prompting Copilot, clarity regarding data sources is paramount. You should explicitly reference the specific files, meeting transcripts, or organizational contexts you wish to query. Because Copilot operates within enterprise security boundaries, prompts must be designed to respect data access permissions and synthesize information from multiple internal enterprise repositories into actionable professional deliverables. When working with Anthropic Claude models, the architecture demonstrates exceptional nuanced reasoning, document synthesis, and adherence to complex, long-form guidelines. Claude models are particularly responsive to XML tag structuring. Enclosing your system instructions, background context, reference data, and output examples within explicit XML tags, such as opening and closing tags for context, instructions, and examples, allows Claude to parse hierarchical relationships with remarkable precision. Furthermore, Claude models excel at extended reasoning workflows when provided with dedicated scratchpad tags. By instructing Claude to write its raw thoughts, verification steps, and preliminary outline inside an internal scratchpad block before producing the final user-facing response, you achieve an extraordinary level of analytical depth and reduce logical errors in complex multi-step tasks. To visualize how cross-platform adaptation works in practice, consider adapting a complex code refactoring prompt across these ecosystems. For OpenAI, you structure the request using a developer system prompt defining strict code quality standards. Supply the code payload in the user message, and enforce a JSON output schema containing the refactored code and an array of modified function signatures. For Google Gemini, you take advantage of its long context by passing the entire codebase repository into the context window, using system instructions to guide Gemini attention across cross-file dependencies and multimodal architectural diagrams. For Microsoft Copilot, you frame the prompt within the enterprise workspace, referencing internal coding standards documents stored on SharePoint and instructing Copilot to generate a pull request summary formatted for corporate code review tools. For Anthropic Claude, you encapsulate the coding guidelines within policy XML tags, the legacy code within source XML tags, and instruct the model to perform an architectural review inside Scratchpad XML tags before generating the refactored code inside Solution XML tags. When designing enterprise prompt architectures, engineers must choose between the megaprompt pattern and the modular prompt chaining pattern. A megaprompt attempts to encapsulate an entire multi-stage business process within a single massive prompt payload. While convenient for rapid prototyping, megaprompts suffer from instruction dilution, high token costs on retries, and poor debuggability when intermediate steps fail. In contrast, the modular prompt chaining pattern decomposes the process into a pipeline of smaller, highly specialized prompts. Each individual prompt operates on a focused subtask, such as data extraction, policy validation, or executive synthesis. If the extraction step fails, the system retries only that lightweight prompt, preserving compute resources and providing granular observability across each step in the pipeline. Furthermore, advanced security architectures implement canary token verification to detect prompt extraction and data exfiltration attacks. In a canary verification setup, the application injects a unique, cryptographically random string, known as a canary token, into the system instructions alongside a strict negative constraint forbidding the model from ever outputting that token. When an adversarial user attempts to execute a system prompt extraction attack, the output is intercepted by a middleware security filter. If the canary token is detected in the generated completion, the filter immediately blocks the response, logs a security alert, and terminates the session, preventing proprietary system instructions from being exposed. Additionally, engineers must consider cross-lingual prompting dynamics. Because transformer foundation models align abstract concepts in shared high-dimensional vector spaces, language models exhibit remarkable cross-lingual transfer capabilities. However, complex multi-step reasoning tasks perform with significantly higher accuracy when prompted in high-resource languages with dense representation in the training corpus, such as English. For global applications operating across low-resource languages, optimal performance is achieved by instructing the model to conduct its intermediate chain of thought reasoning in English inside an internal scratchpad, before generating the final customer-facing output in the target local language. A transformative advancement in production prompt engineering is the architecture of prompt caching. In traditional API architectures, every incoming request processes the entire prompt payload from scratch, recomputing key-value activations for long system instructions, policy documents, and few-shot exemplars on every single turn. Prompt caching systems, available across major foundation model providers, allow the graphics hardware to persist the computed KV cache of static prompt prefixes in GPU memory across consecutive API calls. When an application sends a request with an identical system instruction and reference documentation prefix, the inference engine skips the computational forward pass for those cache tokens, loading their pre-computed KV cache directly from memory. Prompt caching slashes time to first token latency by up to 80% and reduces API costs for static context by up to 90%. To maximize prompt caching efficiency, software engineers structure prompts so that all static, unchanging content, such as system policies and documentation, is placed at the very beginning of the prompt payload, while dynamic, turn-specific user data is appended at the terminal position. When prototyping and testing prompts before committing them to code-based repositories, software engineers rely on developer playground environments. Interactive playgrounds allow engineers to adjust temperature sliders, test different system instructions, inspect raw logit probability outputs, and compare responses across different model versions side by side. Furthermore, engineering teams implement prompt versioning systems integrated with version control workflows. Treating prompts as living software artifacts requires tracking changes via commit histories, maintaining semantic release tags, and executing automated regression tests whenever a prompt template is modified, ensuring that updates to production prompts follow the exact same engineering discipline as compiled application code. By understanding these platform-specific nuances alongside universal prompting mechanics, you can design prompts that reliably extract maximum intelligence, accuracy, and efficiency from any foundation model architecture. Now that we have explored how to construct individual prompts, we must examine the broader environment in which those prompts operate, the critical discipline of providing and managing context. In generative artificial intelligence engineering, there is a fundamental axiom that every practitioner eventually discovers. The quality of the context provided to a model is almost always more influential than the wording of the prompt itself. To understand why this is true, we must look at how the attention mechanism operates mathematically. When you submit a request, your prompt represents only a tiny fraction of the total token sequence evaluated by the transformer. The surrounding context, which includes background documentation, system parameters, conversational history, and reference data, establishes the multidimensional probability landscape across which the self-attention heads compute their weights. If you provide a brilliant prompt with flawless grammar and precise instructions, but supply it with noisy, incomplete, or ambiguous context, the model is mathematically forced to sample from a distorted probability distribution. Conversely, if you provide a relatively simple prompt accompanied by pristine, highly structured, and relevant reference context, the model effortlessly converges on an accurate, high-fidelity response. Context is the anchor that pins the model probabilistic sampling to your specific reality. This dynamic introduces the critical concept of the signal-to-noise ratio in context engineering. Every single token introduced into the context window consumes a portion of the model computational attention. Transformer attention is not an infinite resource. It is a distributed probability distribution that must sum to exactly 1 across all tokens in the sequence. When you flood the context window with hundreds of lines of extraneous metadata, verbose system logs, redundant conversational greetings, or irrelevant document sections, you introduce noise into the vector space. These unnecessary tokens create competing attention sinks. During the self-attention calculations, the query vectors of your core task will inevitably calculate non-zero dot products against the key vectors of that irrelevant data, diluting the attention allocated to the critical instructions. To maximize the signal-to-noise ratio, you must practice disciplined context curation. You must include precise definitions of domain entities, explicit operational rules, verified reference facts, and the exact raw data required to solve the problem. Simultaneously, you must ruthlessly eliminate boilerplate text, repetitive headers, conversational pleasantries, and tangential background information that does not directly contribute to resolving the objective. In production engineering, advanced pipelines employ contextual compression and semantic pruning frameworks, such as LLM Lingua. A semantic pruning engine utilizes a compact, highly efficient language model to calculate the perplexity and information density of every token in a long context document. Tokens that contribute low information density, such as repetitive grammatical fillers, predictable prepositions, and redundant phrasing, are pruned from the sequence before being sent to the primary foundation model. This allows engineering systems to compress massive documents by up to 50% without losing critical factual semantics, dramatically accelerating inference speeds and slashing API costs. Once you have identified the essential information, the next engineering challenge is determining how to structure that context effectively. The physical arrangement and demarcation of data within the context window significantly impacts model comprehension. Unstructured text that blends instructions, data, and constraints into a continuous narrative creates semantic ambiguity. The model attention heads must work to distinguish where a business rule ends and where a customer transcript begins. To resolve this ambiguity, you should always employ clear structural delimiters and semantic tagging. Enclosing distinct data types within explicit boundaries, such as labeled markdown blocks or XML tag pairs, creates sharp semantic edges in the embedding space. When you wrap reference documentation inside opening and closing documentation tags, and wrap user input data inside dedicated input tags, you provide clear structural markers that the attention mechanism can utilize to separate operational commands from the data being operated upon. This prevents data leakage, where the model mistakenly interprets content inside a customer document as an instruction to be executed rather than text to be analyzed. Furthermore, you must consider the spatial positioning of information within the context window, a phenomenon governed by what researchers describe as the attention distribution curve or the lost in the middle phenomenon. Extensive empirical evaluations of transformer neural networks have demonstrated that models do not distribute their attention uniformly across long sequences. Instead, the attention curve typically follows a U-shaped distribution. Models exhibit exceptionally high recall and adherence for information placed at the very beginning of the context window, known as primacy bias, and for information placed at the very end of the context window, known as recency bias. Information situated deep in the middle of a massive context window is statistically more likely to be overlooked or underweight during the self-attention process. When a model processes a 50-page document, a subtle constraint located on page 25 faces a higher probability of retrieval failure than an instruction placed on page 1 or page 50. To engineer around this architectural reality, you should adopt a strategy of strategic anchoring. Place your highest priority behavioral rules, system roles, and foundational definitions at the very top of the context payload. Place your extensive reference documents and raw input data in the middle section. Finally, place your active task prompt, key formatting schemas, and critical negative constraints at the very bottom of the payload, directly preceding the point where the model begins generating its completion. By placing the operational command at the terminal position, the model attention heads immediately link the active query with the instructions while the recency effect is at its absolute peak. To master context engineering, you must also understand the physical and computational constraints of context windows, as well as the hardware mechanisms used to manage them. Every language model is defined by a maximum context window limit, which represents the total number of tokens the model can evaluate in a single forward pass, including both the input prompt and the generated response. These limits range from several thousand tokens in smaller, specialized models to hundreds of thousands or even millions of tokens in massive foundation architectures. However, expanding the context window introduces severe computational and hardware trade-offs. In the standard vanilla transformer architecture, the computational complexity and memory requirements of self-attention scale quadratically, represented mathematically as big O of n squared, where n is the number of tokens in the sequence. To understand why this scaling is quadratic, consider how self-attention works. Every single token must calculate a dot product against every other token in the sequence. If you double the sequence length from 4,000 tokens to 8,000 tokens, the total number of attention calculations does not merely double, it quadruples. If you increase the sequence length by a factor of 10, the attention computation increases by a factor of 100. In addition to processing power, long contexts place immense pressure on graphics processing unit memory through the key-value cache, commonly known as the KV cache. During autoregressive generation, when the model predicts tokens one by one, it does not recompute the mathematical representations of all previous tokens from scratch for every single step. Doing so would be computationally prohibitive. Instead, The system stores the computed key and value vectors of all preceding tokens in graphics processing unit memory. This stored memory buffer is the KV cache. To grasp the magnitude of this hardware footprint, consider the mathematics of KV cache memory consumption. For a model with dozens of transformer layers, dozens of attention heads, and high-dimensional vector representations, every single token in the context window consumes dozens of kilobytes of high-bandwidth memory. When processing a sequence of 100,000 tokens across multiple concurrent user requests, the KV cache alone can consume hundreds of gigabytes of high-bandwidth memory. For enterprise deployments serving thousands of users simultaneously, KV cache memory consumption quickly exhausts available GPU RAM, resulting in memory allocation failures, severe queuing delays, and exponential increases in operational infrastructure costs. To overcome these physical hardware limits, artificial intelligence researchers and hardware engineers have developed advanced architectural optimizations. Techniques such as flash attention optimize how data is transferred between high-speed on-chip SRAM memory and high-capacity GPU memory, dramatically accelerating attention computation without changing the mathematical output. Paged attention divides the KV cache into non-contiguous memory blocks, eliminating memory fragmentation and allowing multiple generation threads to share cache memory efficiently. Architectures have also shifted from standard multi-head attention to multi-query attention and grouped query attention. In grouped query attention, multiple query heads share a single key and value head, drastically reducing the physical size of the KV cache in memory while preserving model reasoning performance. When designing software systems that interact with generative models, engineers must implement explicit context management strategies to operate efficiently within these boundaries. The first strategy is conversational windowing and rolling history management. In a multi-turn chat application, sending the entire raw history of every user message and assistant reply on every turn quickly consumes the context window and drives up inference costs. To manage this, engineers implement sliding window buffers or rolling summarization pipelines. A sliding window buffer retains only the most recent end turns of the conversation in full detail, discarding older messages once they exceed a defined token threshold. For applications requiring long-term conversational memory, a rolling summarization pipeline utilizes a secondary, lightweight model call in the background. When the conversation reaches a certain length, the system takes the oldest conversational turns, generates a dense, factual summary of the key decisions, entities, and context established in those messages, and prepends that condensed summary to the top of the context window. This preserves critical historical context while freeing up thousands of tokens for ongoing interaction. The second and most widely adopted enterprise architecture for context management is retrieval-augmented generation, commonly known as RAG. Retrieval-augmented generation solves the fundamental tension between context window limits, knowledge freshness, and hallucination prevention. Instead of attempting to cram an entire enterprise knowledge base, product catalog, or legal library directly into the model context window, RAG decouples information storage from language reasoning. In a RAG architecture, external knowledge documents are first processed through a chunking pipeline. The documents are broken down into manageable, semantically coherent passages, typically ranging from a few hundred to 1,000 tokens. The design of the chunking strategy is critical. A naive fixed-size chunking algorithm that splits text every 500 words can inadvertently sever a sentence in half or separate a table header from its rows, destroying semantic coherence. To prevent this, Advanced pipelines implement recursive character chunking or document structure-aware chunking. Recursive chunking attempts to split text along natural document boundaries, such as double line breaks between paragraphs, single line breaks between sentences, and punctuation marks, preserving the internal integrity of thoughts. Furthermore, chunking algorithms apply a sliding window overlap, typically between 10 and 20% of the chunk size. By duplicating the final 50 or 100 tokens of chunk A at the beginning of chunk B, the pipeline ensures that semantic context spanning across boundary lines is not lost during vectorization. Furthermore, semantic chunking analyzes the cosine distance between the embedding vectors of consecutive sentences, creating chunk boundaries only when a significant shift in topic is detected. Each text chunk is then passed through an embedding model, which converts the text into a dense mathematical vector. Modern embedding models utilize Matryoshka representation learning, which trains embeddings so that information is densely packed into the initial dimensions. This allows engineers to truncate a high-dimensional vector, such as reducing it from 1,500 dimensions to 500 dimensions, slashing vector database storage and search latency by 60% while retaining over 98% of retrieval accuracy. These vectors, along with the raw text chunks and their associated metadata, are stored in a specialized database known as a vector database. Within the vector database, high-dimensional vectors are organized using specialized indexing algorithms such as hierarchical navigable small world graphs or inverted file indexing with product quantization. Hierarchical navigable small world graphs organize multidimensional vectors into a multi-layered geometric graph, similar to an express highway network. The top layers contain long-range links that allow search algorithms to leap across large semantic distances, while bottom layers contain dense local connections for granular nearest neighbor discovery. Inverted file indexing with product quantization divides high-dimensional vectors into smaller subvectors and clusters them into discrete Voronoi cells. During search, the database evaluates only the centroids of nearby clusters, enabling lightning-fast approximate nearest neighbor searches across hundreds of millions of vectors while fitting entirely within standard system RAM. When a user submits a query to the system, the RAG pipeline does not send the query directly to the generative language model. First, it passes the user query through the exact same embedding model to generate a query vector. The system then performs a semantic similarity search across the vector database, comparing the query vector against the indexed document vectors using mathematical distance metrics such as cosine similarity or Euclidean distance. This identifies candidate document chunks that are semantically most relevant to the user query. To achieve maximum accuracy, modern enterprise RAG systems frequently employ hybrid search architectures. Hybrid search combines dense vector retrieval, which captures high-level conceptual meaning and semantic intent, with sparse keyword retrieval algorithms like BM25, which excel at finding exact terminology, serial numbers, product codes, and proper nouns. The retrieved candidate chunks from both dense and sparse searches are merged using reciprocal rank fusion, an algorithmic scoring method that normalizes and combines the rankings from disparate search engines. These combined passages are then passed through a re-ranking model. The re-ranker is a specialized cross-encoder neural network. While embedding models evaluate queries and documents independently as single vectors, a cross-encoder evaluates the query and document chunk simultaneously through all transformer attention layers, computing full token-to-token attention. This produces an exceptionally accurate relevance score, reordering the candidate passages based on true contextual relevance. For applications requiring extreme precision, architectures utilize late interaction retrieval models like Colbert. Unlike single-vector embedding models that compress an entire paragraph into a single vector, Colbert retains token-level embeddings for both queries and documents. During retrieval, Colbert computes token-to-token similarity using a maxim operator, capturing fine-grained phrase alignments that standard dense embeddings often compress away. Beyond standard RAG, advanced retrieval patterns solve complex edge cases. One such pattern is hypothetical document embeddings, known as HYDE. When a user submits an abstract or exploratory question, comparing that short question vector directly against dense document passages can produce poor retrieval results because questions and answers occupy different syntactic spaces in the embedding manifold. HYDE resolves this by first prompting a generative model to produce a hypothetical, zero-shot answer to the question. Even if this hypothetical answer contains minor factual errors, its vocabulary and thematic structure closely match the text of real answer documents. The system then embeds this hypothetical answer and uses its vector to search the database, dramatically improving retrieval accuracy on complex domain queries. Another advanced pattern is parent-child document retrieval. In parent-child retrieval, large documents are split into large parent chunks, such as entire chapters or sections, and each parent chunk is further subdivided into small child chunks, such as individual paragraphs. The vector database indexes the small child chunks for semantic search. When a user query matches a child chunk, the system does not return just that isolated paragraph. It retrieves and passes the entire parent chunk into the model context window. This guarantees that the retrieval search is highly granular and precise, while the context provided to the generative model is rich, complete, and fully contextualized. Additionally, contextual chunk headers can be applied during document ingestion. When splitting a 500-page technical manual into chunks, a paragraph on page 200 describing an error code might not mention the specific machine model it applies to. By utilizing an automated model to prepend a concise header to every chunk specifying the document title, chapter topic, and parent section, the semantic embedding captures the full context of the passage, preventing retrieval failures. To scale context windows to millions of tokens across distributed hardware clusters, researchers developed ring attention. In standard distributed architectures, processing a sequence of millions of tokens on a single graphics processing unit is impossible due to memory limits. Ring attention partitions the long sequence across a circular ring of multiple GPUs. Each GPU holds a slice of the token sequence and computes attention locally. Simultaneously, key and value tensors are passed around the ring in a peer-to-peer communication loop, overlapping tensor communication with self-attention computation. This allows models to scale their effective context window linearly with the number of available GPUs, unlocking the ability to process entire libraries of books or hours of high-definition video in a single inference pass. Furthermore, complex research queries frequently require multi-hop retrieval decomposition. When an engineer asks a question that depends on multiple interconnected facts, such as how does the latency of our new caching layer affect our end-to-end payment processing SLA, a single vector search query often fails because no single document contains both topics together. A multi-hop retrieval controller first decomposes the complex question into independent subqueries. The first query retrieves technical documentation regarding the caching layer latency metrics. The retrieval engine ingests those findings and automatically formulates a second query targeting the payment processing SLA documentation. The system then merges the findings from both retrieval hops, allowing the generative model to execute flawless cross-domain deductive reasoning. Furthermore, advanced enterprise architectures implement Graph RAG, which integrates structured knowledge graphs alongside vector databases. In a Graph RAG system, an extraction pipeline identifies entities, organizations, concepts, and their explicit relationships across an entire document corpus, storing them in a graph database. When a user asks a complex multi-hop question, such as how does a supply disruption at a specific subcontractor impact our quarterly hardware delivery timeline, vector search alone often fails because the relevant facts are scattered across 20 unrelated documents. A knowledge graph traverses the semantic edges connecting the supplier to intermediate logistics nodes and final product assemblies. The system retrieves this structured relational subgraph and feeds it into the generative model alongside dense text passages, enabling flawless multi-hop causal reasoning across enterprise knowledge networks. Moreover, modern systems implement self-RAG and corrective RAG. In self-RAG, the generative model outputs internal reflection tokens indicating whether retrieved context is relevant, factual, or useful. If the model determines that retrieved passages are insufficient or contradictory, a corrective RAG controller automatically rewrites the query and executes an external web search to augment the internal knowledge base before generating the final response. Finally, the top-ranked, contextualized passages are dynamically injected into the context window of the generative language model, wrapped inside structured reference tags alongside the user original query and strict system instructions. The system instruction directs the model to answer the user query relying exclusively on the provided reference passages, explicitly instructing it to state that the information is unavailable if the answer cannot be derived directly from the provided text. In large-scale enterprise graph RAG architectures, knowledge graph construction relies on advanced community detection algorithms, such as the Leiden algorithm. When thousands of entity nodes and relationship edges are extracted from enterprise document repositories, the knowledge graph is partitioned into hierarchical semantic clusters or communities. A high-level community might represent an entire product ecosystem, while subcommunities represent specific software modules or supply chain dependencies. An automated summarization pipeline generates hierarchical community summaries at every level of the graph. When a user submits an overarching thematic question, such as summarize our enterprise cybersecurity posture across all cloud infrastructure, the Graph RAG system does not query individual text chunks. Instead, it retrieves the high-level community summaries across the graph, providing a comprehensive, holistic synthesis that standard vector search across isolated paragraphs cannot achieve. Furthermore, production vector databases optimize query latency and throughput through GPU-accelerated indexing and distributed sharding. Vector databases partition high-dimensional vector indexes across distributed compute clusters, utilizing GPU-accelerated nearest neighbor libraries like Raft and CUVS to parallelize distance calculations across thousands of CUDA cores simultaneously. This enables sub-millisecond query execution across datasets containing billions of high-dimensional vectors, ensuring that retrieval pipelines scale effortlessly under high-concurrency enterprise workloads. By implementing retrieval-augmented generation, you transform the large language model from an unreliable, closed-book factual database into a powerful, open-book analytical reasoning engine. The model is no longer required to recall obscure facts from its frozen internal parameters. Instead, it reads fresh, verified enterprise context provided on the fly, dramatically reducing hallucinations, eliminating knowledge cutoff limitations, and ensuring that every generated response is verifiable, auditable, and grounded in ground truth data. As foundation models evolve to support ultra-long context windows spanning hundreds of thousands or millions of tokens, a common architectural question arises. Should an engineering team use long context prompting directly, or should they implement a RAG pipeline? The answer lies in evaluating the fundamental engineering trade-offs between latency, operational cost, retrieval precision, and computational scope. Direct long context prompting is ideal for comprehensive, holistic analysis of a specific, bounded dataset. If you need to analyze an entire quarterly financial filing, compare 3 legal contracts simultaneously, or ingest an entire software codebase to plan a major architectural refactoring, passing the entire body of text directly into a long context model allows the self-attention mechanism to compute relationships across all sections of the document at once. There is no risk of a chunking algorithm splitting a critical sentence in half, and the model has access to the complete narrative structure. However, long context prompting carries significant operational costs. Processing 1 million tokens through a large foundation model requires substantial graphics processing unit memory, introduces noticeable latency delays before the first token is generated, and incurs high monetary costs per API call. If you have an enterprise library containing millions of documents across thousands of subjects, feeding the entire library into every user prompt is technically impossible and economically non-viable. Retrieval-augmented generation remains the optimal architectural choice for large-scale, open-ended knowledge discovery across massive, dynamic datasets. RAG enables fast, cost-effective queries by retrieving only the precise paragraphs needed to answer a specific question, keeping prompt payloads compact and response times near real-time. By mastering the mechanics of context curation, structural demarcation, spatial anchoring, and retrieval architectures, you gain total control over the operational environment of generative models. However, even with flawless context, no generative artificial intelligence system is infallible. To build resilient and trustworthy applications, we must implement rigorous methodologies for reviewing, verifying, and improving model outputs. A critical milestone in the development of an artificial intelligence practitioner is the transition from naive trust to a rigorous zero-trust evaluation mindset. When interacting with generative artificial intelligence, human operators are uniquely vulnerable to the illusion of linguistic fluency. Because foundation models generate prose that is grammatically flawless, highly articulate, and delivered with an authoritative tone, human psychology instinctively equates that eloquence with intellectual competence and factual accuracy. In human communication, someone who speaks with absolute confidence and sophisticated vocabulary is typically well-informed. In large language models, however, fluency is merely a reflection of statistical pattern matching across syntax. A model can construct an entirely fictional legal precedent, describe a non-existent chemical reaction, or invent an imaginary software library with the exact same syntactic beauty and unwavering confidence that it uses to explain basic laws of physics. Blindly trusting generative output in production systems, analytical reports, or technical development creates severe systemic vulnerabilities. A single unverified hallucination in a financial analysis can lead to flawed investment strategies. An undetected syntax hallucination in an automated deployment script can bring down production infrastructure, and an unverified claim in a medical or legal document can introduce catastrophic liability. To safeguard against these failure modes, engineers must establish systematic verification and fact-checking methodologies. The first methodology is the principle of deterministic execution validation. Whenever a generative model produces structured logic, such as software code, database queries, mathematical calculations, or configuration files, the output must never be evaluated solely by human visual inspection. It must be executed inside a deterministic, sandboxed environment equipped with automated verification tests. If a model generates a Python script to perform statistical data transformation, you should pass that code into an isolated container that runs an automated test suite verifying edge cases, boundary conditions, and null value handling. If a model performs complex arithmetic or algebraic manipulations, you should route those calculations to a symbolic mathematics engine or an external calculator tool rather than accepting the token-level predictions of the neural network. By offloading validation to deterministic compilers and interpreters, you eliminate the risk of subtle logic errors slipping into production. The second methodology is counterfactual probing and self-critique. Large language models possess vast latent knowledge that can be utilized to evaluate their own intermediate work if prompted through a separate, dedicated critique step. After generating a comprehensive technical design or analytical recommendation, you can submit the generated output back to the model with an adversarial evaluation rubric. Instruct the model to act as a hostile security auditor or a skeptical principal engineer whose sole objective is to identify potential failure modes, hidden assumptions, edge case vulnerabilities, and factual ambiguities within the text. Because this critique prompt shifts the attention heads toward vulnerability detection rather than solution generation, the model often reveals critical blind spots that were overlooked during the initial generation pass. The third methodology is multimodal cross-evaluation and triangulation. Different foundation model families are trained on distinct datasets, utilize different tokenization schemes, and undergo unique alignment and fine-tuning procedures. Consequently, they rarely share the exact same blind spots or hallucination profiles. In high-stakes enterprise workflows, passing the output of one model architecture to an independent model architecture alongside a rigorous scoring rubric provides an effective layer of automated quality control. If a model developed by one organization synthesizes a complex document and an independent model developed by another organization flags a specific assertion as unsupported by the provided context, the discrepancy immediately flags the passage for human expert review. The fourth methodology is round-trip verification and semantic backtranslation. When extracting complex facts or synthesizing dense technical reports, you can verify semantic integrity by passing the generated summary to a separate model instance and asking it to reconstruct the core premises or quantitative figures without seeing the original source document. Comparing the reconstructed premises against the original source text reveals whether the model accurately captured the fundamental meaning or if subtle semantic drift occurred during generation. If critical quantitative metrics or causal relationships are distorted in the round-trip reconstruction, the output is flagged for manual correction. Furthermore, in production software engineering, teams implement comprehensive automated evaluation metric suites. Classical natural language evaluation metrics such as BLEU and Rouge evaluate n-gram overlap between generated text and reference text. While computationally lightweight, these lexical metrics fail to capture semantic equivalence. A sentence expressing the exact same idea using different synonyms often receives a penalizingly low BLEU score. To overcome this, modern systems utilize embedding-based metrics like BERT score, which computes token-level cosine similarity in vector space, rewarding semantic fidelity even when phrasing differs. To evaluate models at an ecosystem scale, the artificial intelligence research community utilizes standardized benchmark suites. Understanding these benchmarks allows engineers to interpret model leaderboards objectively. Prominent benchmarks include massive multitask language understanding, which evaluates world knowledge across dozens of academic and professional subjects, HumanEval and SWE-Bench, which evaluate functional software engineering and autonomous GitHub issue resolution, and GSM-8K and Math, which evaluate multi-step mathematical and algorithmic deduction. Additionally, crowdsourced blind evaluation ladders, such as the chatbot Arena ELO ratings, measure human preference win rates across thousands of head-to-head model completions. However, public benchmarks suffer from dataset contamination, where benchmark questions inadvertently leak into pre-training corpora. Consequently, enterprise engineering teams construct internal, proprietary evaluation suites reflecting their specific domain data and business logic. For complex analytical tasks, engineering teams rely on LLM as-a-judge frameworks such as GEval. In an automated evaluation harness, incoming model completions are scored against defined rubrics covering factual accuracy, tone adherence, schema validity, and context relevance. The evaluation engine can run both reference-based evaluations, comparing model outputs against human-verified gold standard answers, and reference-free evaluations, assessing logical consistency and constraint adherence directly. To deploy LLM as-a-judge pipelines reliably, engineers must account for and mitigate inherent judge biases. The first bias is position bias, where an evaluating model tends to favor the first option presented when comparing two candidate responses. To neutralize position bias, evaluation pipelines run pairwise comparisons twice, swapping the presentation order of the candidates and averaging the resulting scores. The second bias is verbosity bias, where language models systematically assign higher quality scores to longer, more elaborate responses, even when a shorter answer is more concise and accurate. Calibrated evaluation prompts explicitly instruct the judge model to penalize conversational filler and reward direct conciseness. The third bias is self-enhancement bias, where models frequently award higher scores to completions generated by their own model family. Utilizing an ensemble of diverse judge models from different providers eliminates single-vendor favoritism and produces an objective consensus evaluation score. By building automated continuous integration and continuous delivery regression test suites, engineering teams maintain curated golden datasets of hundreds of representative domain prompts and edge cases. Whenever a system prompt, retrieval chunking parameter, or underlying foundation model version is updated, the test suite executes automatically, calculating pass rates, latency metrics, and ELO rating comparisons before deploying changes to production. To ensure that automated LLM as-a-judge pipelines correlate strongly with human ground truth, engineering teams measure interannotator agreement metrics such as Cohen's kappa or Fleisch kappa. In an alignment calibration study, human domain experts and automated judge models evaluate the same set of model completions against a standardized rubric. If the statistical agreement score between human judges and the automated model exceeds 0.8, the judge prompt is certified for automated production testing. If the agreement score is low, the rubric instructions are iteratively refined with explicit evaluation criteria and few-shot calibration examples until high statistical alignment is achieved. Additionally, production systems track model confidence calibration curves using metrics like the Breyer score and expected calibration error. A well-calibrated model assigns probability scores that accurately reflect true correctness likelihood. If a model assigns an 80% confidence score to a prediction, that prediction should be empirically correct 80% of the time. When models exhibit poor calibration, engineers apply temperature scaling and Platt scaling transformations to recalibrate confidence estimates, ensuring that automated systems can reliably identify when an output requires human expert review. To guarantee the resilience of production prompt pipelines, quality assurance teams implement automated synthetic perturbation testing. In a perturbation testing harness, an automated testing framework takes a verified golden dataset and injects realistic real-world noise into the inputs. The framework generates hundreds of variations containing typographical errors, synonym substitutions, transposed sentence clauses, dialect variations, and extraneous conversational filler. The pipeline processes these perturbed inputs and evaluates whether the output accuracy, schema validity, and factual consistency remain stable. If a minor syntactic alteration causes the foundation model to fail a business constraint or hallucinate a data field, the prompt is identified as fragile, prompting engineers to strengthen system guardrails and formatting delimiters before deploying to production. In automated testing environments, generating reliable test assertions for non-deterministic language models requires the design of automated test oracles. Because generative models rarely produce identical text across consecutive runs, traditional string equality assertions fail. Instead, test oracles execute multidimensional invariant checks, verifying that all required JSON keys exist, that numerical values fall within acceptable physical bounds, that forbidden keywords are absent, and that semantic similarity against reference solutions exceeds statistical thresholds. These invariant checks allow automated testing pipelines to evaluate thousands of synthetic test runs continuously, providing software teams with high confidence before deploying model updates to production. When an initial model output falls short of requirements, the engineer must decide how to iterate and refine the response effectively. A common mistake during iteration is submitting vague expressions of dissatisfaction, such as "this is not what I wanted," or "make it better." These inputs provide no actionable signal, forcing the model to guess which dimension of the response requires modification. Instead, you should employ targeted delta prompting. Targeted delta prompting isolates the precise variance between the actual output and the desired outcome. You identify the exact paragraph, code block, or conceptual assertion that requires alteration, state the specific reason for the deficiency, and provide explicit correction criteria. For example, if a model generates a software architecture document that relies on synchronous HTTP communication between microservices, your iteration prompt should state that synchronous communication introduces tight coupling and latency bottlenecks, and instruct the model to refactor the design to utilize an asynchronous message broker with event-driven consumer workers. By providing explicit technical direction, you guide the model attention heads directly toward the required architectural pattern. Furthermore, when dealing with multivariable deficiencies, you should employ conversational pivoting, isolating each issue and resolving it sequentially rather than attempting to correct 5 unrelated flaws simultaneously. Adjust the underlying data structure first, verify its integrity, then adjust the algorithm logic, and finally refine the stylistic presentation. However, during this iterative cycle, you will inevitably encounter a critical decision point. Should you continue correcting the existing conversation, or is it time to abandon the session and start over with a clean slate? To make this decision correctly, you must understand the mechanics of context contamination and attention poisoning. Every time an interaction occurs in a conversational thread, the entire history of user prompts, assistant replies, and intermediate corrections remains inside the active context window. If the model generates a deeply flawed response in turn 2, that incorrect response and all the tokens describing its flaws become permanent reference material for all subsequent forward passes. Even if you issue a sharp correction in turn 3, the attention mechanism still computes dot products against the faulty tokens from turn 2. The presence of the erroneous text creates a persistent drag on the model reasoning. In complex tasks, the model often becomes trapped in a cycle of defensive hallucinations, apologizing profusely while repeatedly reintroducing the same underlying error in slightly different variations. This state is known as attention poisoning. When the context window becomes cluttered with failed attempts, contradictory instructions, and lengthy apologies, the signal-to-noise ratio collapses. The model attention heads become saturated with the very errors you are trying to eliminate. As an engineer, you must recognize when attention poisoning has occurred. If a model fails to correct an architectural or factual mistake after 1 or 2 explicit delta prompts, continuing the conversation is counterproductive. The optimal strategy is to wipe the slate clean. Open a new, unpolluted session. Take the lessons learned from the failed interaction, refine your original system instructions, inject explicit negative constraints addressing the specific failure mode you observed, provide a concrete few-shot example demonstrating the correct approach, and submit the refined prompt as a fresh single-turn request. By resetting the context window, you eliminate all historical noise, restoring the full computational power of the attention mechanism to focus exclusively on the correct solution path. Mastering these verification and refinement workflows ensures that your interactions with generative systems remain rigorous, objective, and resilient. However, building reliable artificial intelligence systems requires more than technical accuracy. It demands an uncompromising commitment to security, privacy, and ethics. As generative artificial intelligence transitions from experimental prototypes into mission-critical enterprise infrastructure, the engineering discipline surrounding ethics, privacy, safety, and governance becomes just as vital as model accuracy and performance. Deploying probabilistic systems that process human language and make decisions introduces complex risk surfaces that traditional software architectures rarely encounter. In classical software engineering, security vulnerabilities typically stem from deterministic software bugs such as buffer overflows, SQL injection, or misconfigured access control lists. In generative systems, the vulnerability surface expands to include the probabilistic, non-deterministic nature of the neural network itself. To build secure and ethical artificial intelligence architectures, we must begin with the foundational challenge of data privacy and the protection of sensitive information. When an organization integrates large language models into its daily operations, vast streams of proprietary data flow into the system. This includes employee communications, proprietary software source code, customer support transcripts, financial projections, medical records, and legal briefs. The primary risk in this pipeline is unauthorized data ingestion and training data leakage. Consumer-facing artificial intelligence services frequently utilize submitted user prompts and conversational interactions to train future iterations of their foundation models. If an engineer pastes proprietary source code containing cryptographic keys or trade secrets into a consumer chat interface, that code can become absorbed into the model weights during subsequent training runs. Once information is encoded into the weights of a large neural network, It is virtually impossible to selectively delete or extract without completely retraining the model from scratch at massive computational expense. In subsequent deployments, adversarial users can craft extraction prompts that trigger the model to recite verbatim passages of that proprietary training data, resulting in catastrophic intellectual property exposure. To prevent this vulnerability, enterprise architectures must enforce strict data governance boundaries. Organizations must utilize dedicated enterprise API endpoints backed by formal zero data retention agreements. Under a zero data retention policy, the artificial intelligence vendor explicitly guarantees that incoming prompt payloads and outgoing completions are processed purely in volatile memory for the duration of the inference request, and are never logged to persistent disk, monitored by human reviewers, or utilized for future model training. For organizations handling ultra-sensitive data, architectures implement confidential computing with hardware-based secure enclaves. In a confidential computing deployment, model inference executes inside physically isolated, cryptographically encrypted processor memory that prevents even the cloud infrastructure provider from inspecting data during execution. Furthermore, resilient engineering architectures implement robust client-side and middleware data sanitization pipelines before prompts ever reach an external API. Imagine a middleware proxy server that intercepts all outbound requests before they leave the corporate firewall. This proxy runs automated scanning algorithms, utilizing regular expressions, named entity recognition models, and cryptographic secret scanners to detect personally identifiable information such as national identity numbers, payment card details, email addresses, medical terminology, and internal system credentials. When sensitive data is detected, the middleware sanitizes the payload through irreversible hashing, structural masking, or token substitution. Instead of sending an employee real name and social security number, the system replaces them with generic placeholders, such as user alpha and identifier 1. The generative model processes the request using these anonymized placeholders, and when the completion returns, the proxy server securely maps the placeholders back to their original values before presenting the final result to the user. Additionally, data privacy engineering incorporates differential privacy principles during model fine-tuning. Differential privacy injects calibrated mathematical noise into training gradients, ensuring that while the model learns general statistical patterns across a private dataset, the presence or absence of any single individual record cannot be mathematically reconstructed from the model parameters. Beyond privacy, we must address the fundamental challenge of algorithmic bias and cultural representation in generative models. Large language models are pre-trained on massive corpora of text scraped from the public internet, digitized books, academic repositories, and open code repositories. While this breadth of data provides the model with impressive linguistic fluency, it also encodes all the historical prejudices, demographic imbalances, cultural stereotypes, and systemic inequalities embedded within human history. If a model training data predominantly represents perspectives from a specific geographic region or socioeconomic demographic, the model attention mechanisms will internalize those cultural norms as the statistical baseline of human thought. When asked to generate a story about a software executive, the model may default to predicting male pronouns. When asked about support staff, it may default to female pronouns. And when asked to evaluate complex cultural or philosophical questions, it may present regional viewpoints as universal truths. Furthermore, bias manifests in representation gaps, where specialized domain terminology, regional dialects, and minority languages have lower token densities in the training corpus. When a model processes a low-resource language, The tokenizer is forced to break words into tiny character fragments, driving up inference costs, increasing latency, and significantly degrading the model reasoning capability compared to high-resource languages. Mitigating these biases requires sophisticated interventions across every stage of the model lifecycle. During pre-training, data engineers utilize automated filtering, demographic balancing, and synthetic data augmentation to ensure diverse representation across cultures, professions, and languages. During the alignment phase, researchers employ reinforcement learning from human feedback and direct preference optimization to steer the model away from harmful stereotyping. In reinforcement learning from human feedback, human annotators score multiple model completions based on helpfulness, accuracy, and safety. A separate reward model is trained on these human preferences, which is then used to update the foundation model weights through reinforcement learning algorithms. However, alignment introduces its own subtle trade-offs. The demographic and cultural background of the human annotators hired to evaluate completions inevitably shapes the model behavioral boundaries. If alignment teams are homogeneous, their collective biases dictate what the model considers polite, offensive, or controversial. To establish more transparent and objective alignment, modern research utilizes constitutional AI. In constitutional AI, engineers define an explicit, transparent constitution containing principles of human rights, fairness, non-maleficence, and objective neutrality. During training, the model is prompted to critique and revise its own preliminary outputs against this explicit constitution, creating a verifiable and auditable alignment pipeline that reduces reliance on subjective human scoring. This brings us to the critical engineering domain of transparency and artificial intelligence safety. A foundational challenge in deep learning is the interpretability problem. A modern large language model contains hundreds of billions of numerical parameters distributed across dozens of transformer layers. When the model generates a specific answer, it is mathematically impossible to trace that output to a single logical rule or discrete database record. The knowledge is distributed across polysemantic neurons, where individual neurons activate for multiple unrelated concepts simultaneously. To pierce this black box, researchers are advancing the field of mechanistic interpretability. By training sparse autoencoders on the internal activation states of transformer layers, engineers can decompose complex neural activations into human interpretable features. This allows safety researchers to observe when a model activates internal concepts related to deception, biological threats, or unauthorized system access before the model ever outputs a single token of text. Furthermore, enterprise software engineering incorporates standardized transparency documentation through model cards and system cards. A model card serves as the formal technical specification for a foundation model, detailing its training data composition, evaluation benchmarks across diverse demographic groups, known performance limitations, recommended operational parameters, and explicit out-of-scope use cases. System cards describe the overarching multi-model deployment environment, documenting data retention policies, moderation filters, and security perimeters. Simultaneously, engineers must defend generative architectures against adversarial attacks, the most prevalent of which are prompt injection vulnerabilities. Prompt injection occurs when an attacker crafts a malicious input designed to hijack the model reasoning, bypass system guardrails, and force the model to execute unauthorized instructions. Prompt injection manifests in several sophisticated forms. Direct prompt injection, often called a jailbreak, occurs when a user directly interacts with the model and uses clever conversational framing to override system instructions. Attackers utilize techniques like greedy coordinate gradient optimization, which generates non-intuitive mathematical token sequences that mathematically force the model attention layers into affirmative generation states. Indirect prompt injection is far more dangerous in enterprise environments. Indirect injection occurs when a model is connected to external data sources through web browsing, document retrieval, or automated email processing. An attacker embeds malicious instructions inside an external document, such as a white-on-white text block on a public web page, an invisible comment inside a PDF resume, or an instruction hidden within a customer support ticket. When an autonomous system reads that document to generate a summary, the model's self-attention mechanism ingests the hidden attack payload. The model mistakenly interprets the attacker text inside the document as an authoritative command from the system operator, causing it to exfiltrate private user data, delete cloud database records, or send unauthorized emails on behalf of the user. Defending against prompt injection requires a defense-in-depth architecture. You must never rely on simple system prompt instructions alone to enforce security, because a sufficiently sophisticated adversarial input can almost always confuse the attention mechanism. Instead, production systems employ multi-layered security perimeters. Incoming user inputs and retrieved external documents are first passed through specialized, lightweight classifier models, such as Llama Guard, trained specifically to detect adversarial patterns, privilege escalation attempts, and malicious syntax. Furthermore, outputs generated by the foundation model must pass through deterministic output guardrails, such as NEMO guardrails, that scan for data leakage, unauthorized API commands, and security policy violations before the output is returned to the user or passed to downstream execution systems. To ensure provenance and content authenticity, modern platforms implement digital watermarking and provenance standards, such as SynthID and the Coalition for Content Provenance and Authenticity protocols. Watermarking techniques subtly alter the sampling probabilities of specific tokens during generation according to a secret mathematical pseudorandom key. While the resulting text or media appears completely natural to human readers, an automated detection algorithm can verify the subtle statistical watermark with high mathematical certainty, proving that the content was generated by a specific artificial intelligence model and providing an auditable chain of custody. To maintain comprehensive governance across enterprise systems, organizations implement automated red teaming fuzzing pipelines. In an automated red teaming harness, specialized adversarial language models are trained via reinforcement learning to generate thousands of creative, multi-turn attack vectors, testing the target system for policy violations, prompt injection vulnerabilities, data leakage, and toxic completion triggers. The target system responses are evaluated by automated safety classifiers, mapping vulnerabilities to specific risk categories and generating automated security heat maps. Whenever a vulnerability is discovered, the development team updates defensive guardrails and adds the adversarial prompt to the continuous integration regression test suite, ensuring proactive vulnerability remediation before deployment. Furthermore, enterprise data governance incorporates cryptographic data provenance tracking. Every training dataset, fine-tuning corpus, and reference document ingested into enterprise pipelines is cryptographically hashed, time-stamped, and recorded on immutable audit ledgers. This guarantees that if a copyright claim or regulatory audit arises, the organization can provide mathematical proof of data lineage, demonstrating exactly what data was used to train specific models and verifying compliance with intellectual property standards. Equally important to knowing how to secure artificial intelligence is knowing when not to use artificial intelligence at all. Generative models are probabilistic, non-deterministic engines designed for semantic transformation, creative synthesis, and ambiguous pattern matching. Deploying them in environments that demand absolute mathematical determinism, zero tolerance for error, and hard real-time latency guarantees is a catastrophic architectural anti-pattern. To structure these decisions, software architects align systems with international regulatory risk frameworks, such as the European Union AI Act risk tiers. The first tier encompasses unacceptable risk applications, such as cognitive behavioral manipulation, social scoring systems, and real-time biometric identification in public spaces, which are strictly prohibited. The second tier covers high-risk applications, including critical infrastructure management, medical diagnosis assistance, educational grading, employment candidate screening, and credit underwriting. In high-risk domains, artificial intelligence systems must undergo strict conformity assessments, maintain detailed logging, ensure robust data governance, and incorporate mandatory human oversight. The third tier covers limited risk applications, such as consumer chatbots, which require explicit transparency disclosures informing users that they are interacting with an artificial intelligence system. The fourth tier covers minimal risk applications, such as spam filters, video game artificial intelligence, and automated document reformatting, which operate with standard software engineering practices. Consider hard real-time mission-critical systems such as commercial aviation flight control systems, autonomous vehicle collision avoidance triggers, medical life support hardware controllers, and nuclear reactor cooling regulators. These systems operate on strict millisecond-level time horizons where an algorithm must guarantee a provably correct, deterministic response under all operating conditions. Introducing a non-deterministic neural network that might experience variable latency or generate a stochastic error is fundamentally unacceptable. Similarly, generative models must never be used as sole-source decision-makers in high-stakes legal adjudication, criminal sentencing, or fully automated loan denial systems where human rights, due process, and legal explainability are mandatory. A model cannot provide a legally binding causal explanation for why it rejected a specific applicant over another. Moreover, for bounded, closed-domain problems where classical algorithms exist, using an artificial intelligence model is an expensive and inefficient design choice. If you need to find the shortest path between two network nodes, sort a database of millions of records, or calculate tax liability based on explicit statutory tables, classical graph algorithms, relational database queries, and deterministic rule engines will solve the problem in microseconds with mathematical perfection and negligible computational cost. Using a billion-parameter language model to perform these tasks introduces latency, immense financial cost, and the risk of hallucination. Ultimately, the deployment of artificial intelligence systems rests on human responsibility and accountability. An artificial intelligence model is a tool, not a legal or moral entity. It cannot bear liability, it cannot sign contracts, and it cannot be held accountable for harm. Whenever an artificial intelligence system makes an error, leaks sensitive data, or generates defamatory content, legal and ethical responsibility rests entirely with the humans who designed, deployed, and authorized the system. To maintain organizational accountability, enterprises must implement robust human-in-the-loop governance frameworks. High-impact operations, such as executing financial transactions, deploying code to production infrastructure, publishing public communications, or altering medical treatment plans, must require explicit human review and cryptographic authorization. The artificial intelligence should act as an analytical assistant that drafts proposals, synthesizes options, and highlights trade-offs. But the ultimate authority and accountability must remain firmly in human hands. Having established these rigorous principles of ethics, safety, and governance, we can now transition from standalone conversational interactions to the architecture of automated, multi-step artificial intelligence workflows. The transition from amateur artificial intelligence usage to professional software engineering is defined by a single conceptual shift, moving away from monolithic, ad hoc conversational prompts and embracing structured, deterministic artificial intelligence workflows. When casual users interact with a generative model, they almost always attempt to solve complex, multi-stage problems in a single prompt. They paste a 30-page document, request a comprehensive strategic analysis, ask for code implementations, demand edge case evaluations, and specify complex formatting rules all within a single request. In production engineering, this monolithic approach is a recipe for failure. When you overload a single forward pass with multiple conflicting objectives, the self-attention mechanism is forced to divide its computational capacity across numerous disparate tasks. The result is predictable: high hallucination rates, shallow reasoning, missed constraints, and broken output formats. An artificial intelligence workflow resolves this bottleneck by decomposing a complex, recurring objective into a sequence of discrete, specialized, and verifiable computational stages. Instead of asking one model to perform 10 tasks simultaneously, an engineered workflow chains together multiple focus prompts, deterministic software functions, and automated validation gates. Each step in the pipeline is given a single, highly constrained responsibility, with the output of one stage serving as the structured input for the next. To design an effective workflow, you must understand the architectural spectrum of pipeline topologies. The simplest topology is the linear pipeline, where data flows sequentially from stage A to stage B to stage C. For example, raw customer feedback is first translated into a common language, then passed to a second stage that extracts key product issues into structured JSON, and finally passed to a third stage that drafts a summary report. A more sophisticated topology is the branching directed acyclic graph. In a directed acyclic graph workflow, the system dynamically routes data down different processing paths based on intermediate classifications. An incoming customer email might first be evaluated by a routing model that determines whether the query concerns technical billing, software bugs, or general feedback. Depending on this classification, the payload is directed down completely different subpipelines equipped with specialized reference documentation and tailored validation rules. Another essential topology is the fan-out fan-in or MapReduce architecture. When processing a massive dataset, such as an archive of 100 customer interviews or 50 legal depositions, passing the entire corpus into a single prompt causes severe context dilution. In a fan-out architecture, deterministic code splits the dataset into 50 independent tasks and dispatches 50 parallel model calls simultaneously. Each worker model extracts key facts into a standardized JSON schema. Once all worker calls complete, a fan-in aggregator model ingests the 50 structured summaries and synthesizes a master executive report. This parallelization slashes end-to-end execution time and ensures deep analytical coverage across every individual document. The most advanced topology is the stateful iterative loop. In an iterative workflow, a model output is subjected to an automated evaluation step. If the output fails to meet predefined quality metrics or schema requirements, the pipeline routes the output back to the model alongside explicit error feedback, allowing the system to refine and correct its work autonomously across multiple controlled iterations. The cornerstone of workflow engineering is establishing a strict boundary between probabilistic artificial intelligence steps and deterministic classical software operations. A common engineering anti-pattern is attempting to force a generative language model to perform tasks that classical software handles with absolute mathematical perfection. You should never use a large language model to perform arithmetic, sort database arrays, validate email regex formats, execute database queries, or calculate date differences. Deterministic software code should handle all data retrieval, format normalization, schema validation, mathematical computation, database reads and writes, and API communications. Generative models should be reserved strictly for operations that require semantic understanding, natural language synthesis, unstructured entity extraction, cross-domain translation, and qualitative reasoning. By confining the generative model to semantic tasks and surrounding it with deterministic software wrappers, you build a resilient hybrid system that leverages the fluid intelligence of neural networks while maintaining the rigorous reliability of traditional software engineering. To understand how these principles function in practice, let us dissect the 4 core architectural phases of an engineered artificial intelligence workflow. Input normalization, semantic transformation, automated validation, and human-in-the-loop review. The first phase is input normalization. Raw data arriving from the real world is messy, unstructured, and often contains irrelevant noise. Before passing an input to a language model, deterministic software should sanitize and standardize the data. This involves stripping extraneous HTML tags, removing duplicate whitespace, truncating log files to relevant time windows, and executing privacy masking scripts to redact sensitive personal information. Normalizing the input ensures that the model context window is populated exclusively with high-value semantic signal. The second phase is semantic transformation. In this phase, one or more specialized prompts process the normalized data. Crucially, each prompt is designed to produce structured, machine-readable output, typically conforming to a strict JSON schema. Rather than generating conversational prose, the model outputs structured key-value pairs that isolate specific facts, classifications, or generated text components. The third phase is automated validation. Once the model outputs its response, deterministic code intercepts the payload before it can proceed to downstream systems. The code validates that the output is valid JSON, verifies that all mandatory schema fields are present and correctly typed, and executes business logic assertions. For example, if the model extracted numerical line items from an invoice, deterministic code immediately sums those line items and verifies that they equal the extracted total invoice amount. If the validation check fails, the pipeline does not crash. Instead, an automated retry mechanism triggers a targeted delta prompt, passing the invalid JSON and the exact validation error back to the model for immediate correction. The fourth phase is human-in-the-loop governance. While automated validation catches structural and mathematical errors, certain operations carry significant legal, financial, or operational consequences that require human judgment. In a well-engineered workflow, the pipeline executes all heavy data gathering, synthesis, drafting, and validation automatically, and then pauses at a designated human checkpoint. The system presents the prepared deliverable alongside source citations and confidence scores to a human expert through an administrative interface. With a single click, the human reviewer can approve the action, make minor manual edits, or reject the proposal, ensuring that human accountability remains intact while slashing operational overhead. To solidify these concepts, let us walk through comprehensive, real-world case studies demonstrating applied artificial intelligence workflows across diverse enterprise domains. Our first case study is a multi-stage technical writing and editorial review pipeline. Consider an engineering organization that needs to transform raw system architecture notes and pull request logs into polished, comprehensive technical documentation for external developers. In stage 1 of the pipeline, deterministic software extracts the raw commit messages, pull request descriptions, and inline code comments from the version control repository. An input normalization script cleans the text, removes automated merge messages, and structures the data chronologically. In stage 2, a specialized extraction model reads the normalized logs and outputs a structured JSON payload identifying the core architectural modifications, new API endpoints, deprecated features, and potential breaking changes. In stage 3, an outlining model takes the structured JSON and generates a detailed, multi-section documentation outline conforming to the company technical style guide. In stage 4, a drafting model processes each section of the outline independently. By generating one section at a time, the model dedicates its full context window and attention capacity to explaining that specific component in exhaustive technical depth, incorporating audio-friendly explanations and mental models. In stage 5, the compiled draft is passed to an adversarial review model acting as a skeptical principal engineer. This model is prompted to scrutinize the draft specifically for technical inaccuracies, missing prerequisites, ambiguous instructions, and inconsistencies between sections. In stage 6, a final polish model ingests the draft alongside the adversarial critique, applying necessary corrections and refining the prose to ensure an authoritative, crystal-clear tone. The final document is then pushed to a human documentation lead for final review and publication. Our second case study is a research synthesis and literature aggregation pipeline. Imagine an academic or corporate research team tasked with monitoring hundreds of scientific white papers, technical preprints, and patent filings published across their industry. In stage 1, an automated ingestion crawler downloads the latest published documents in PDF format, converts them into clean markdown text, and splits them into logical sections including abstracts, methodologies, results, and discussions. In stage 2, each paper is passed through an extraction prompt that outputs a standardized JSON summary capturing the core hypothesis, experimental methodology, sample sizes, quantitative benchmark results, and stated limitations. In stage 3, the structured summaries of all reviewed papers are aggregated and passed into a comparative analysis model. This model constructs a cross-paper synthesis matrix, identifying converging consensus trends, contradictory findings across different research groups, and unexplored gaps in the literature. In stage 4, a synthesis model compiles the comparative matrix into an executive research briefing, complete with direct citations pointing back to specific page numbers and document identifiers. A deterministic script verifies that every cited claim corresponds to an actual extracted sentence in the source database, eliminating hallucinated citations before delivering the briefing to senior research scientists. Our third case study is an unstructured data extraction and enterprise database pipeline. Consider a logistics and supply chain enterprise that receives thousands of supplier invoices, shipping manifests, and customs declarations daily via email in diverse, non-standardized formats including scanned PDFs, spreadsheet attachments, and body text. In Stage 1, an optical character recognition and document layout engine extracts the raw text and visual bounding boxes from incoming attachments. In Stage 2, an extraction model guided by few-shot examples and a rigid JSON schema extracts critical business entities: supplier name, tax identification number, invoice date, currency, individual line items with quantities and unit prices, applied discounts, and total payable amount. In Stage 3, deterministic validation code executes rigorous financial assertions. The code verifies that multiplying each line item quantity by its unit price equals the stated line total, that summing all line totals minus discounts plus taxes equals the invoice grand total, and that the extracted supplier tax number matches an active record in the corporate vendor database. If a mathematical discrepancy or unknown vendor is detected, the pipeline automatically flags the invoice, creates an exception ticket in a dead letter queue, and routes the original document and extracted fields to an accounts payable specialist. If all deterministic checks pass with zero discrepancies, the data is automatically committed to the enterprise resource planning database, and an automated payment schedule is queued without requiring manual data entry. Our fourth case study is a customer communications triage and escalation pipeline. Imagine a high-volume consumer software platform receiving tens of thousands of customer support inquiries daily across email, chat widgets, and social channels. In Stage 1, an incoming message is ingested and normalized. In Stage 2, a classification model analyzes the text to determine primary intent, customer sentiment, urgency level, and whether the message indicates potential customer churn or legal escalation. In Stage 3, an entity extraction model pulls out customer identifiers, account numbers, error codes, and referenced features. Deterministic software takes these extracted identifiers and queries internal telemetry databases, retrieving the user current subscription tier, recent billing history, and active error logs from the server infrastructure. In Stage 4, an orchestration model ingests the customer original inquiry alongside their live account context and the relevant internal troubleshooting documentation. The model drafts an empathetic, highly specific response that directly addresses the root cause of the error based on server telemetry. In Stage 5, the pipeline evaluates the response against an automated risk matrix. If the customer is an enterprise tier client, if the sentiment is highly negative, or if the issue involves financial refunds, the draft response and telemetry summary are routed to a senior support engineer for one-click review and personalization. If the inquiry is a standard informational question from a free tier user and the model confidence score exceeds 98%, the validated response is dispatched automatically, dramatically reducing ticket resolution times while maintaining consistent support quality. Our fifth case study is an automated legal contract compliance and risk analysis pipeline. In a global enterprise negotiating hundreds of vendor agreements and master services contracts simultaneously, manual legal review creates severe operational bottlenecks. In Stage 1 of the contract pipeline, incoming contracts in PDF format are converted to clean text and parsed into structured contractual clauses using structural layout analysis. In Stage 2, a specialized clause extraction model maps each clause against standard corporate legal categories, such as indemnification, limitation of liability, intellectual property ownership, confidentiality, and termination rights. In Stage 3, a legal risk analysis model compares the extracted terms against the company's standard fallback positions. The model flags non-standard clauses, identifies high-risk liability caps, and detects ambiguous jurisdictional provisions, generating a structured risk scorecard. In Stage 4, a redlining model drafts proposed counterprovisions conforming to standard company language, generating inline explanation notes detailing the business justification for each modification. In Stage 5, the complete contract package, risk scorecard, and proposed red lines are delivered to the corporate legal counsel for strategic negotiation, accelerating contract review cycles from weeks to minutes while enforcing consistent corporate risk governance. Our sixth case study is an autonomous software vulnerability triage and patch pipeline. In a modern software security operations center, thousands of automated dependency alerts and vulnerability reports are generated across hundreds of microservices. In Stage 1, security alerts from static analysis tools and vulnerability scanners are ingested and deduplicated. In Stage 2, an analysis model reads the vulnerability report alongside the specific vulnerable function in the corporate codebase to determine whether the vulnerable code path is actually reachable and exploitable within the application runtime context. In Stage 3, if the vulnerability is confirmed reachable, a patch generation model ingests the vulnerable source code, unit test suites, and the security advisory guidelines to draft a targeted code fix that remediates the vulnerability without altering existing functional behavior. In Stage 4, an isolated continuous integration sandbox compiles the patched code and executes the complete regression test suite. If tests fail or new compiler errors emerge, an automated retry loop feeds the compiler errors back to the model to refine the patch. In Stage 5, once all regression and security unit tests pass with 0 errors, the pipeline automatically opens a pull request in the version control system, attaching the vulnerability analysis, test results, and patch description, awaiting final approval from the engineering security lead. To make these automated pipelines reliable at scale, software engineers rely on repeatable infrastructure patterns. Prompt templates are parameterized using template engines, allowing dynamic runtime variable injection without string concatenation errors. Structured outputs are validated using strict schema enforcement libraries, guaranteeing that data flowing between pipeline nodes conforms to exact type definitions. Furthermore, production pipelines implement semantic caching using high-speed in-memory data stores like Redis. When an incoming prompt is semantically identical or nearly identical to a previously processed request, the system retrieves the cached response instantly, eliminating redundant model inference, slashing latency to single-digit milliseconds, and reducing API costs by up to 40%. Deployment of prompts in enterprise pipelines follows standard software engineering practices, including canary deployments and shadow testing. When a prompt is updated, the new version is deployed in shadow mode, running in parallel with the production prompt against live traffic without serving results to users. The engineering team compares output distributions, latency, and error rates before gradually shifting live traffic to the new prompt version. Additionally, production systems implement automated fallback mechanisms. If a primary foundation model experiences an API outage or latency spike, a circuit breaker trips and automatically routes traffic to a secondary foundation model provider with adapted prompt parameters, ensuring continuous high availability. High-throughput distributed systems utilize event streaming platforms like Apache Kafka and distributed task queues like Celery. When thousands of complex requests arrive concurrently, the message broker buffers the requests into partition queues, distributing tasks across worker nodes that manage token rate limits, enforce concurrency boundaries, and record distributed telemetry traces across every node in the execution graph. In distributed enterprise environments, workflow state management is governed by persistent checkpointing architectures. When a multi-stage workflow processes long-running asynchronous tasks spanning hours or days, intermediate state dictionaries are continuously serialized and persisted to durable storage backends, such as PostgreSQL or Redis. If a server node crashes or experiences a network partition mid-execution, the workflow orchestrator reads the serialized checkpoint, reestablishes the exact execution state, and resumes processing from the last validated node without re-executing expensive upstream artificial intelligence steps. Furthermore, checkpointing enables time travel debugging, allowing engineers to inspect the exact state variables, prompt payloads, and model completions at any point in the workflow execution history. When evaluating and monitoring production artificial intelligence pipelines, systems engineers track three fundamental operational latency metrics. The first metric is time to first token, which measures the elapsed time from when an API request is dispatched to when the first completion token is streamed back to the client. This metric reflects prompt processing time, context ingestion speed, and queuing delays. The second metric is time per output token, which measures the generation latency between consecutive tokens during autoregressive decoding. This metric is primarily governed by model parameter size, GPU memory bandwidth, and batch concurrency. The third metric is overall system throughput, measured in total tokens processed per second across concurrent client sessions. By tracking these metrics through distributed tracing dashboards, engineering teams can identify performance bottlenecks, optimize batch sizes, select appropriate quantization levels, and ensure that real-time user experiences remain responsive and seamless. Across different platforms, these workflows can be implemented through diverse technical architectures. Within consumer and productivity suites, workflows can be constructed using custom GPTs, workspace projects, and low-code visual workflow builders. These interfaces allow non-technical teams to chain system prompts, attach specific knowledge bases, and integrate webhooks to automate routine office tasks. In enterprise software engineering, workflows are constructed programmatically using foundation model software development kits, asynchronous message queues, and dedicated orchestration frameworks. Engineers write robust back-end services in languages like Python or TypeScript, utilizing distributed task queues to handle rate limiting, token budgeting, retry back-off logic, and end-to-end telemetry monitoring across thousands of concurrent execution pipelines. By designing modular, verifiable, and resilient artificial intelligence workflows, you transform generative models from unpredictable conversational novelty into powerful, industrial-grade software engines. However, as software pipelines become more sophisticated, we encounter tasks where predefined, rigid linear workflows are insufficient. This brings us to the frontier of autonomous artificial intelligence systems, the emergence of agents. To understand where the software industry is heading, we must examine the evolutionary continuum of artificial intelligence architectures. This continuum progresses through three distinct levels of capability: the standalone prompt, the structured workflow, and the autonomous agent. At the first level is the standalone prompt. A prompt is a passive, single-turn transaction. You provide an input, the model performs a single forward pass through its neural network, and it returns a completion. The model has no autonomy, cannot interact with the external world, cannot verify its output against live data, and relies entirely on the human operator to direct every subsequent action. At the second level is the structured workflow. As we explored, a workflow chains multiple prompts and deterministic software functions into a predefined execution graph. The system follows fixed, human-engineered pathways, routing data through validation checks and specialized subtasks. While workflows are vastly more reliable and capable than standalone prompts, their execution path is rigid. If the system encounters an unforeseen scenario that was not explicitly hard-coded into its routing logic, the workflow cannot adapt. It simply fails. At the third level is the autonomous artificial intelligence agent. An agent represents a fundamental architectural leap from static execution to dynamic, goal-directed problem-solving. Instead of following a rigid, predefined sequence of steps, an agent is provided with a high-level objective, an operational environment, a set of available software tools, and an autonomous decision-making loop. The agent evaluates the current state of its environment, formulates a plan, selects and executes an appropriate tool, observes the outcome of that action, reflects on whether the action brought it closer to the goal, and dynamically adjusts its subsequent steps until the objective is accomplished. To visualize how an agent operates, imagine a skilled software engineer sitting at a computer terminal tasked with fixing a bug in an unfamiliar codebase. The engineer does not know the exact sequence of commands they will execute before they begin. Instead, they operate through an iterative loop. They search the file tree to locate the relevant source code, read the file contents, write a failing unit test, modify the implementation, run the test suite, observe the compiler error, correct the syntax, and rerun the tests until everything passes. An autonomous artificial intelligence agent implements this exact cognitive loop through software architecture. At the heart of modern agent design is the React framework, an architectural paradigm that interleaves reasoning and acting. In a React loop, the agent executes 4 continuous, cyclic phases: thought, action, observation, and reflection. In the thought phase, the foundation model evaluates its high-level objective alongside the conversational history and current environmental state. The model generates internal reasoning tokens, explicitly articulating what it knows, what information is missing, and what intermediate step it must take next. In the action phase, the model decides to interact with the external world. Because a language model cannot directly execute code or call operating system functions on its own, it utilizes tool calling, also known as function calling. Modern agent platforms standardize tool discovery and invocation through unified protocols such as the Model Context Protocol. The Model Context Protocol establishes an open client-server architecture for artificial intelligence systems. A centralized agent host connects to multiple distributed MCP servers via JSON RPC transport layers. Each server exposes explicit resources, structured prompt templates, and executable tools. This decouples tool development from model logic, allowing an agent to dynamically query server registries, inspect available tool schemas, and execute functions across disparate software environments without requiring custom hard-coded integrations for every API. The system provides the model with a structured registry of available tools, defined using standardized JSON schemas. These tools might include a web search engine, a database query client, a code execution sandbox, an API caller, or a file system reader. When the model decides to take an action, it does not output conversational text. Instead, it outputs a structured JSON payload specifying the exact name of the tool it wishes to invoke and the precise input parameters required. In the observation phase, the agent-host environment intercepts the model JSON tool call, executes the requested function in the real world, and captures the result. If the agent requested a database query, the host environment runs the query against the database, captures the returned records or error messages, and injects that raw output back into the model context window labeled as a tool observation. In the reflection phase, the model reads the observation returned by the tool. If the action succeeded, the model assesses whether the high-level objective has been fully achieved or if further steps are needed. If the action failed, for example, if an API returned a 404 error or a Python script threw an exception, the model analyzes the error message, updates its internal mental model of the problem, and loops back to the thought phase to formulate an alternative strategy. To make these autonomous loops effective, an agent architecture relies on 4 foundational pillars: planning, memory, tools, and reflection. The planning component is responsible for task decomposition. When faced with a complex objective, such as conduct a comprehensive competitive audit of 3 enterprise software platforms, the planning module breaks the high-level goal into a hierarchical tree of manageable subtasks. Advanced architectures combine tree of thoughts with Monte Carlo tree search to simulate potential execution paths, evaluating expected success probabilities before committing to an action. The memory component provides the agent with continuity across long-horizon tasks. This is typically divided into short-term working memory, episodic memory, and long-term persistent memory. Short-term working memory consists of the active context window, containing the current conversation history, intermediate tool calls, observations, and scratchpad reasoning. Episodic memory records specific past trajectories, errors, and successful execution paths. Through cognitive frameworks like reflection, the agent performs self-evaluations after completing tasks, generating linguistic feedback describing what strategies succeeded and what mistakes occurred. These reflective notes are stored in episodic memory and retrieved during future tasks, allowing the agent to learn from experience without retraining underlying neural weights. Long-term persistent memory utilizes external storage systems, such as vector databases or relational document stores. When an agent discovers important facts or completes subtasks during a multi-hour investigation, it writes summaries of those findings into its long-term memory store. Later in the task, when it needs to recall earlier findings, it queries its memory store via semantic search, retrieving relevant historical context without overflowing its active context window. The tool component acts as the agent hands and eyes in the digital world. By equipping an agent with specialized APIs, file system access, web browsers, and command line execution sandboxes, you transform the model from a passive text predictor into an active operational engine capable of manipulating digital environments. The reflection component enforces quality control and self-correction. Advanced agent architectures implement dedicated reflection modules that continuously evaluate whether the agent's current trajectory is making meaningful progress or if it is stuck in unproductive loops. To coordinate complex multi-step processes, modern software systems utilize state graph architectures, where agent execution is modeled as a state machine. In a state graph, distinct nodes represent specialized cognitive functions, such as planning, research, execution, or validation. The state machine maintains a persistent state dictionary that tracks current variables, execution history, and artifact paths. Edges between nodes represent conditional transitions governed by validation checks. If a code validation node succeeds, the edge transitions to the documentation node. If it fails, the edge loops back to the debugging node with the compiler trace. Furthermore, modern architectures are expanding into multi-agent collaboration frameworks, often referred to as swarm architectures. In a multi-agent system, complex objectives are distributed across specialized agent personas that communicate via a structured message bus. A supervisor agent decomposes the master goal and delegates subtasks to worker agents. A research agent gathers data, a coding agent writes software implementations, an adversarial testing agent executes unit tests and identifies bugs, and an editorial agent compiles the final documentation. Multi-agent debate protocols allow multiple agents to critique and refine each other's proposals independently, filtering out individual hallucinations and arriving at robust consensus decisions. To understand how an autonomous software engineering agent operates in a real environment, consider an automated bug remediation workflow. The agent is given a bug report from an issue tracker. First, the agent queries the file system to locate the relevant source code files and configuration scripts. Second, it creates an isolated Git branch. Third, it writes a reproduction unit test that fails, confirming the bug existence. Fourth, it analyzes the stack trace, modifies the underlying algorithm in the source file, and recompiles the project inside an isolated Docker sandbox. Fifth, it runs the entire test suite, verifying that the new test passes and no existing regression tests break. Sixth, it runs a code linter to format the code to company standards, commits the changes with a descriptive commit message, and opens a pull request, tagging the lead engineer for final review. However, as exciting as autonomous agents are, understanding their current engineering limitations is essential for any realistic system design. The most critical operational vulnerability of autonomous agents is the compounding probability of failure over long execution horizons. In a probabilistic system, every individual decision, tool selection, parameter extraction, and reflection step carries a non-zero chance of error. If an agent has a 95% accuracy rate on each individual step, its probability of executing a 3-step task without error is roughly 86%. However, if a complex objective requires 20 sequential autonomous steps, the cumulative probability of flawless execution drops precipitously to approximately 36%. If the task requires 50 steps, the probability of success falls below 8%. In an agent loop, an uncorrected error at step 5 compounds catastrophically across subsequent steps. If the agent misinterprets an observation early in its execution, all subsequent planning is based on false premises, leading the agent into an inescapable death spiral of nonsensical actions, infinite loops, and massive token consumption. Furthermore, autonomous agents face severe resource and cost challenges. Because every iteration of the thought-action-observation loop requires sending the entire cumulative conversational history back to the foundation model, the context window expands rapidly with every tool call. A complex 20-step task can easily consume hundreds of thousands of tokens, generating significant API costs and latency delays. To deploy agents safely and reliably in enterprise environments, software architects must implement rigorous guardrails and human oversight mechanisms. The first essential guardrail is environment isolation through secure sandboxing. An artificial intelligence agent must never be granted unrestricted execution access to local operating systems, corporate production databases, or open network environments. All tool executions, especially code compilation, shell script execution, and file system operations, must take place inside isolated, ephemeral execution sandboxes such as secure virtual containers or WebAssembly runtimes. These sandboxes enforce strict CPU, memory, and network limits, preventing a malfunctioning or compromised agent from consuming system resources or causing infrastructure damage. The second guardrail is the principle of least privilege for tool access. Tools provided to an agent should have the absolute minimum permissions required to perform their intended function. Database tools should be restricted to read-only queries whenever possible, and network access should be restricted to an explicit whitelist of approved domain endpoints. The third guardrail is the enforcement of hard execution boundaries. Agent architectures must include strict circuit breakers, including hard maximum limits on the number of execution iterations, total execution time, and cumulative monetary cost. If an agent fails to resolve an objective within 15 iterations, the circuit breaker trips, halts execution, and alerts a human operator. The fourth and most vital guardrail is state mutation gating through human authorization. We must distinguish between read-only exploratory actions and state-mutating actions. An agent should be allowed to autonomously search documentation, query databases, read code files, and analyze data in read-only mode. However, whenever an agent proposes an action that permanently alters external state, such as deploying code to production, executing financial transactions, sending emails to external clients, or deleting database records, the execution loop must pause. The agent must present its proposed action, complete with its underlying reasoning and expected impact, to a human supervisor for explicit review and cryptographic sign-off. To manage human oversight smoothly in production environments, agent frameworks utilize automated escalation matrices and asynchronous webhook gates. Rather than requiring human intervention for every minor action, an escalation matrix assigns dynamic risk scores to prospective tool calls based on their potential blast radius. Read-only queries to public databases carry a risk score of 0, allowing the agent to proceed autonomously. Actions involving modifications to internal staging environments carry moderate risk scores, requiring automated secondary model verification. High-risk actions, such as executing financial transfers, modifying production firewall rules, or sending customer-facing communications, automatically trigger an execution interrupt. The agent runtime serializes its execution state, generates a concise human-readable summary of the proposed action and its underlying rationale, and dispatches an asynchronous webhook to an enterprise collaboration platform or security operations center. Once a human supervisor reviews the request and cryptographically signs the authorization token, the webhook returns the approval signal, allowing the agent runtime to resume its cognitive loop seamlessly. Across the artificial intelligence industry, architectural philosophies regarding agent implementation are beginning to diverge. One school of thought champions centralized, monolithic reasoning models. Proponents of this approach argue that foundation models will internalize long-horizon planning, error correction, and multi-step reasoning natively within their neural weights, requiring minimal external scaffolding. Another school of thought advocates for modular, multi-agent swarm architectures. In a multi-agent system, a complex objective is distributed across a team of specialized, lightweight agents. One agent acts as a project manager, another acts as a research specialist, a third writes code, and a fourth acts as a dedicated quality assurance tester. These agents collaborate by passing structured messages back and forth through a shared communication bus. Simultaneously, the industry is seeing a divergence between centralized, cloud-hosted enterprise agent platforms and local, edge-based autonomous agents running directly on developer workstations and local hardware clusters. Cloud platforms offer massive compute scale and integrated enterprise data access, while local edge architectures provide unmatched data privacy, zero latency over local networks, and complete autonomy from third-party API dependencies. In advanced multi-agent swarm architectures, agent coordination is modeled through structured communication topologies. In a hierarchical supervisor topology, a master planning agent receives the overarching goal, breaks it into discrete work packages, and assigns them to worker agents, maintaining strict quality control over all intermediate deliverables. In a peer-to-peer gossip topology, specialized agents communicate directly through pub-sub message channels, sharing observations and coordinating actions collaboratively without a single point of failure. In a router consensus topology, multiple independent agents generate diverse candidate solutions in parallel, and a specialized arbiter model evaluates the candidates against objective criteria, selecting or synthesizing the optimal solution. These modular swarm topologies allow software architects to build resilient, distributed artificial intelligence systems that scale gracefully across complex enterprise domains. By mastering the mechanics of planning, memory, tool orchestration, and safety guardrails, you position yourself at the cutting edge of modern software architecture. To build these advanced systems effectively, engineers and practitioners must cultivate deep, verifiable expertise across leading foundational platforms. We will now examine and compare the official educational foundations programs offered by the industry pioneers shaping the artificial intelligence landscape. As artificial intelligence cements its status as foundational technology across global enterprise, the leading research organizations and cloud providers have established official educational pathways and certification programs. Navigating these educational ecosystems is essential for professionals seeking structured, authoritative, and verifiable knowledge. Each major technology provider has designed its curriculum around its distinct architectural strengths, commercial philosophy, and target audience. By analyzing the structural differences between programs from OpenAI, Microsoft, Google, and IBM, you can select the exact educational path aligned with your professional objectives. Let us begin with the official educational ecosystem established by OpenAI. OpenAI provides a multi-tiered learning architecture divided into two primary environments: the public OpenAI Academy platform and the developer-centric API ecosystem. The OpenAI Academy represents OpenAI official public learning hub, offering structured, self-paced courses designed to build practical capability from foundational literacy to advanced operational workflows. The curriculum of the OpenAI Academy is organized into 3 progressive foundational courses. The first course is AI Foundations. This curriculum introduces the core mechanics of artificial intelligence and large language models, focusing on building essential habits for effective prompt construction, providing clear operational instructions, injecting useful reference context, evaluating and fact-checking model outputs, and maintaining responsible usage in daily tasks. The second course is Applied AI Foundations. This curriculum elevates individual prompting into repeatable workflows. Students learn how to decompose complex recurring tasks into structured steps, identify precise intervention points where artificial intelligence excels versus where human expertise is mandatory, and embed verification checkpoints and human-in-the-loop governance directly into the operational process. The third course is Agents and Workflows. This curriculum explores the frontier of autonomous task execution. Students learn how to establish operational boundaries and guardrails for autonomous agents, define strict output constraints, orchestrate multi-step tool interactions, and refine reusable agentic workflow patterns. Complementing the OpenAI Academy, OpenAI maintains its developer-centric educational tracks through developer documentation, the OpenAI Cookbook, and collaborative technical courses with DeepLearning.ai. These technical tracks dive deeply into code-level API primitives, exploring function calling, JSON schema enforcement, dense vector embeddings, fine-tuning methodologies, and production retrieval architectures. Furthermore, OpenAI is expanding its formal certification track. Beyond course completion certificates, formal OpenAI certifications evaluate job-ready professional competency through scenario-based assessments administered directly within enterprise environments. The strength of the OpenAI curriculum lies in its direct connection to state-of-the-art foundation model capabilities, offering an ideal progression for professionals seeking practical workflow mastery, as well as software engineers building custom API-driven applications. In contrast to OpenAI model-centric focus, Microsoft provides an enterprise-wide educational framework centered on workplace productivity, cloud infrastructure, and formal organizational certification. Microsoft offers two distinct educational pathways: the Career Essentials in Generative AI curriculum, developed in partnership with LinkedIn Learning and Microsoft Learn, and the formal Microsoft Certified Azure AI Fundamentals certification, known in the industry as Exam AI 900, and its updated cloud curriculum. The Career Essentials in Generative AI pathway is designed for broad professional artificial intelligence literacy. It focuses on how generative intelligence transforms day-to-day workplace productivity, exploring prompt engineering techniques, automated document synthesis, data visualization, and the core principles of ethical artificial intelligence within the Microsoft Copilot ecosystem without requiring programming prerequisites. The Azure AI Fundamentals certification, by contrast, is a formal, proctored technical credential that validates an engineer understanding of artificial intelligence workloads and cloud implementations across the Microsoft Azure platform. The Azure AI Fundamentals curriculum is organized into 4 core technical domains. Domain 1 evaluates fundamental artificial intelligence concepts, including workload identification and the 6 principles of responsible AI: fairness, reliability and safety, privacy and security, inclusiveness, transparency, and accountability. Domain 2 covers fundamental machine learning principles, exploring regression, classification, and clustering workloads, automated machine learning pipelines, and model evaluation metrics within Azure Machine Learning Studio. Domain 3 covers computer vision workloads, exploring image analysis, facial recognition, spatial analysis, and optical character recognition for automated document processing. Domain 4 covers natural language processing and generative artificial intelligence, exploring sentiment analysis, key phrase extraction, entity recognition, conversational bot frameworks, and the deployment of large language models using Azure OpenAI Service and Microsoft AI Foundry. The Microsoft Learning Path is exceptionally well suited for enterprise systems architects, cloud administrators, IT leaders, and corporate business analysts who operate within enterprise Microsoft 365 and Azure environments and require verifiable, industry-recognized credentials. Google approaches artificial intelligence education by leveraging its deep heritage in academic research, multimodal computing, and scalable cloud machine learning infrastructure. Google distributes its educational programs across 2 primary environments: the Google AI Essentials specialization hosted on Coursera, and the comprehensive generative AI learning paths hosted on the Google Skills platform, formerly known as Google Cloud Skills Boost. Google AI Essentials is a broad, cross-disciplinary foundation course structured into 5 core modules designed for professionals across all industries. Module 1 introduces foundational artificial intelligence concepts, demystifying how models learn patterns from data. Module 2 teaches effective prompt design, demonstrating how to write clear, structured instructions and establish operational constraints. Module 3 explores multimodal tools for workplace productivity, showing students how to synthesize text, create visual assets, and automate repetitive office workflows using Gemini. Module 4 focuses on factual verification and algorithmic bias auditing, teaching students how to identify hallucinations and mitigate demographic skews. Module 5 explores future workplace workflows, emphasizing the ethical stewardship of automated tools. For technical practitioners, Google Cloud Generative AI learning paths on the Google Skills platform offer deep architectural instruction. This curriculum explores the inner workings of transformer architectures, attention mechanisms, and the deployment of foundation models on Google Vertex AI. The curriculum covers Vertex AI model garden curation, prompt design in Vertex AI Studio, multimodal embedding generation, vector search indexing, and grounding generative responses with Google Search Infrastructure. Additionally, engineers learn how to implement reinforcement learning from human feedback on Vertex AI and build scalable enterprise machine learning pipelines. The Google Learning Path is ideal for data scientists, machine learning engineers, cloud developers, and technical practitioners who want to build advanced multimodal applications and leverage scalable cloud machine learning pipelines. IBM delivers an educational ecosystem uniquely tailored for enterprise governance, regulatory compliance, data provenance, and trustworthy artificial intelligence deployments. Through IBM Skills Build and the IBM AI Foundation's professional certificates on platforms like Coursera, IBM focuses heavily on the operational realities of deploying artificial intelligence within highly regulated industries such as banking, healthcare, insurance, and government. The IBM curriculum is structured around the 3 core pillars of the IBM Watsonx platform. The first pillar is watsonx.ai, which teaches practitioners how to access, prompt, and fine-tune foundation models in a secure enterprise studio, selecting domain-specific models tailored for specific industry tasks. The second pillar is watsonx.data, an open data lakehouse architecture that teaches data lineage, access control enforcement, and data curation pipelines to ensure that training data is pristine and legally compliant. The third pillar is watsonx.governance, which provides automated tools to monitor models for fairness, bias drift, explainability, and regulatory compliance throughout the entire artificial intelligence lifecycle. IBM coursework emphasizes compliance with emerging global regulations, such as the European Union AI Act, teaching organizations how to generate automated compliance scorecards and maintain cryptographic audit trails for automated decision systems. Furthermore, when comparing the learning environments across these platforms, hands-on lab architectures play a decisive role. The OpenAI Playground and Academy modules provide clean, interactive web interfaces and local Python notebooks optimized for rapid parameter tuning, structured JSON generation, and direct agent experimentation. Microsoft Learn utilizes browser-based Azure sandboxes that provision temporary cloud resources, allowing students to train machine learning models and configure Azure OpenAI endpoints without incurring personal cloud billing costs. The Google Skills platform provides temporary, fully provisioned Google Cloud Project accounts for each lab session, giving students access to live Vertex AI compute environments and Model Garden repositories. IBM Skills Build and WhatSonks tutorials offer integrated cloud workspaces where enterprise governance tools, bias detection dashboards, and data lakehouse connections can be explored in simulated corporate environments. In addition to foundational and developer tracks, each organization provides specialized enterprise deployment architectures. OpenAI enables enterprise organizations to deploy dedicated private instances through ChatGPT Enterprise and customized workplace workspaces, providing administrative analytics, centralized workspace management, and domain verification controls. Microsoft integrates Azure OpenAI Service with Azure Virtual Networks, private endpoints, managed identities, and customer-managed encryption keys, providing enterprise security perimeters that satisfy rigorous regulatory requirements. Google connects Vertex AI with BigQuery and Google Cloud Security Infrastructure, enabling organizations to train and serve models directly adjacent to enterprise data warehouses. IBM anchors WhatSonks in Red Hat OpenShift hybrid cloud infrastructure, enabling enterprises to run foundation models across on-premises data centers, private clouds, and multi-cloud environments while maintaining complete infrastructure sovereignty. By comparing these four leading ecosystems, a clear taxonomy emerges. If your goal is to master practical workflows, prompt engineering habits, and autonomous agent loops directly from the creators of ChatGPT, alongside deep API development via deeplearning.ai, OpenAI provides the foundational standard. If your goal is to architect enterprise cloud systems, master corporate productivity tools, and achieve a globally recognized cloud credential, Microsoft offers the most structured enterprise pathway. If your goal is to build multimodal applications, explore deep machine learning architectures, and leverage scalable cloud infrastructure, Google delivers unmatched technical breadth. And if your goal is to navigate regulatory compliance, establish rigorous enterprise governance, and deploy auditable, trustworthy systems in regulated industries, IBM provides the definitive blueprint. Understanding the unique focus of each platform enables you to select the precise curriculum that serves your long-term career trajectory. We will now examine the practical logistics of how to access these courses, navigate free versus paid credentials, and acquire official certifications. Translating your understanding of artificial intelligence educational programs into actionable professional credentials requires a clear grasp of how these learning pathways are hosted, funded, and verified. Navigating the landscape of online learning platforms can be confusing, as courses are often distributed across multiple hosting portals with varying pricing tiers, subscription models, and credentialing standards. Understanding the mechanics of course access ensures that you maximize your educational investment while acquiring industry-recognized credentials. To begin, you must know where each platform official curriculum is hosted. OpenAI Foundational Learning is hosted directly on the official OpenAI Academy portal at academy.openai.com. Here, learners can access AI foundations, applied AI foundations, and agents and workflows free of charge. For technical API courses, OpenAI developer guides and collaborative short courses with deeplearning.ai are accessible directly through the Deep Learning AI portal and OpenAI developer documentation. Microsoft Foundational Learning is hosted across two major platforms, Microsoft Learn and LinkedIn Learning. The Career Essentials in Generative AI pathway is available on LinkedIn Learning, with core technical modules mirrored on the free Microsoft Learn documentation platform. Preparation materials, sandbox labs, and practice assessments for the formal Azure AI Fundamentals certification exam are hosted directly on Microsoft Learn. Google distributes its educational pathways across Coursera and the Google Skills platform. The foundational Google AI Essential Certificate is hosted on Coursera, while technical cloud-focused learning paths covering Vertex AI, Gemini, and Transformer architectures are housed on the Google Skills platform. IBM hosts its foundational educational programs through two primary channels: the IBM Skills Build platform, which provides free access to technology education for students, job seekers, and professionals, and the IBM AI Foundation specialization hosted on Coursera. When planning your learning journey, understanding the financial and access models across these platforms is essential. A common misconception is that obtaining world-class education from leading technology companies requires expensive tuition fees. In reality, a vast majority of the core knowledge is accessible completely free of charge if you understand how to navigate platform access settings. On the OpenAI Academy platform, all core courses are completely free for registered ChatGPT users, granting official OpenAI course completion certificates upon finishing each module without requiring subscription fees. On platforms like Coursera and edX, most foundational courses offer a free audit mode. When you enroll in audit mode, you receive complete, unrestricted access to all video lectures, reading materials, and ungraded practice exercises without paying any fee. The only features locked behind the paid tier are graded assignments, automated programming labs, and the final issued certificate of completion. If your primary objective is acquiring knowledge, deep understanding, and practical skills, the free audit mode provides everything you need. Furthermore, several major platforms offer free verified digital badges that carry significant professional weight without requiring any paid subscription. IBM Skills Build offers completely free access to its foundational artificial intelligence curriculum, including graded assessments. Upon completing a learning path, IBM issues a verified digital badge through the Credly credentialing network at zero cost. These digital badges contain verifiable metadata detailing the exact competencies mastered, which can be shared directly on professional resumes and digital portfolios. Similarly, Microsoft Learn provides free interactive learning paths, hands-on sandbox exercises, and knowledge checks. Completing learning modules on Microsoft Learn earns digital trophies and profile badges that demonstrate continuous professional development. On the Google Skills platform, completing hands-on cloud quests and skill assessments earns verifiable Google Cloud Skill badges, demonstrating practical ability to configure Vertex AI pipelines and foundation model deployments. However, if you require a formal, third-party verified credential for corporate compliance, career transitions, or institutional recognition, you should understand the distinction between course completion certificates and proctored certification exams. A course completion certificate, such as those issued by OpenAI Academy, Coursera for Google AI Essentials, or IBM AI Foundations, confirms that you have completed the video lectures and passed the online quizzes within that specific course platform. A proctored industry certification, such as the Microsoft Certified Azure AI Fundamentals exam, operates under a much more rigorous verification standard. To earn a proctored cloud credential, you must register for an official examination through an authorized testing vendor. The exam is administered either in person at an authorized testing center or online under live proctored supervision, where identity verification and strict testing environments are enforced. During the exam, candidates must answer a variety of question formats, including multiple-choice questions, scenario-based architecture evaluations, and drag-and-drop matching exercises covering machine learning workloads, computer vision, natural language processing, and generative model deployments on cloud platforms. Passing a proctored certification proves that you possess verified, independent technical competence that cannot be fabricated through automated scripts or shared answer keys. In enterprise hiring and government contracting, proctored certifications carry substantially higher credibility than standard course completion certificates. To prepare effectively for proctored exams, candidates should complete the official free learning paths on Microsoft Learn, practice with official practice assessments to identify knowledge gaps, and gain hands-on familiarity by creating free trial cloud accounts to explore live services firsthand. To maximize success when preparing for formal certification exams, candidates should adopt a structured 4-week preparation timeline. In Week 1, thoroughly review the official examination skills outline, identifying the core domains and weighting percentages assigned to each topic. Complete the foundational self-paced learning modules to build theoretical vocabulary. In Week 2, focus on hands-on practical exercises. Deploy sample services in free cloud sandbox environments, test API calls, configure data sources, and explore administrative settings to bridge theory with practical reality. In Week 3, take official practice assessments in an untimed environment, analyzing the rationale behind both correct and incorrect answer choices to eliminate conceptual blind spots. In Week 4, take full-length timed mock exams to build endurance and time management discipline, reviewing final summary sheets the day before the examination. Finally, practitioners must establish a strategy for certification maintenance and continuous professional development. In the rapidly evolving field of artificial intelligence, foundational cloud certifications typically feature periodic renewal cycles. Cloud providers like Microsoft offer free annual renewal assessments through Microsoft Learn, allowing certified professionals to maintain their active credential status by verifying their knowledge of newly released cloud services and updated architectural patterns without paying additional exam fees. To select the right educational path and credentialing strategy, you should evaluate your current career role and long-term professional objectives. If you are a software engineer, full-stack developer, or systems programmer, your goal is to demonstrate hands-on implementation capability. Begin with OpenAI Academy courses for workflow mastery, expand into OpenAI and DeepLearning.ai developer masterclasses to master function calling, vector embeddings, and API orchestration, and augment this with Google Skills Pathways on Vertex AI to understand cloud deployment. Rather than collecting numerous introductory certificates, your strongest credential is a public, open-source portfolio demonstrating functional artificial intelligence workflows and agentic pipelines. If you are an enterprise cloud architect, systems engineer, or IT administrator, your career thrives on formal cloud platform mastery. Your ideal path is preparing for and passing the Microsoft Certified Azure AI Fundamentals exam. This provides an industry-standard credential verifying your ability to design, govern, and deploy artificial intelligence workloads within enterprise cloud architectures. If you are an enterprise compliance officer, risk manager, legal counsel, or data governance director, your focus is risk mitigation, data sovereignty, and regulatory readiness. The IBM AI Foundations and IBM Skills Build Pathways provide the specialized vocabulary, audit frameworks, and governance models necessary to oversee corporate compliance in highly regulated environments. If you are a business leader, project manager, or knowledge worker looking to enhance daily productivity, the OpenAI Academy AI Foundations Pathway, Google AI Essentials Program, and Microsoft Career Essentials Pathway offer the perfect balance of practical prompt engineering, workplace automation strategies, and responsible usage principles. By aligning your learning pathway with your strategic career goals and leveraging free audit modes, digital badges, and formal proctored certifications, you establish a verified, highly credible foundation in artificial intelligence engineering. When showcasing your certifications to prospective employers or clients, presentation strategy is critical. Digital badges earned through Credly for IBM Skills Build or Microsoft Learn should be embedded directly into digital resumes and online professional profiles, ensuring that hiring managers can click to verify the underlying metadata, issuing authority, and validated skill domains. For developer-oriented credentials, such as OpenAI Academy course certificates or Google Cloud Skill badges, pair the certificate with an active GitHub repository demonstrating functional implementation code, such as a custom retrieval pipeline, an autonomous tool calling agent, or a structured workflow parser. Providing verifiable code alongside official credentials delivers definitive proof of engineering capability. With our complete roadmap from physical neural mechanisms to enterprise certifications established, let us conclude by synthesizing the core mental models that will guide your journey forward. Congratulations on completing this comprehensive masterclass on the foundations of generative artificial intelligence. By investing the time to deconstruct these complex systems from mathematical foundations to high-level enterprise architectures, you have established a mental model that places you ahead of the vast majority of technology practitioners. Throughout this masterclass, we have moved beyond surface-level hype and casual conversational tricks to examine the true engineering realities of artificial intelligence. Let us synthesize the essential mental models and key takeaways that will serve as your permanent operational foundation. First, remember the true nature of a large language model. It is not a conscious entity that possesses subjective thoughts, personal beliefs, or independent intent. It is a high-dimensional probabilistic engine that transforms words into mathematical vectors and computes the path of highest statistical plausibility through autoregressive next-token prediction. Recognizing this distinction frees you from the illusion of linguistic fluency, allowing you to anticipate limitations, understand the mathematical roots of hallucinations, and design systems that channel statistical probability into deterministic reliability. Second, always prioritize context over raw prompt phrasing. Your prompt is merely the final spark, but the context establishes the entire thermodynamic landscape of the neural network. By curating pristine, high-signal reference materials utilizing structural delimiters like XML tags, respecting the attention distribution curve, and implementing retrieval architectures like RAG, you anchor the model sampling directly to verified ground truth. Third, approach prompt design with the discipline of software engineering. Leverage system messages to establish permanent behavioral policies. Enforce rigid, machine-readable JSON output schemas to eliminate conversational noise. Provide few-shot demonstration pairs to lock in complex patterns, and utilize chain-of-thought prompting to expand the model internal computational capacity on complex reasoning tasks. Fourth, maintain an uncompromising zero-trust evaluation posture. Never assume that syntactic eloquence equates to factual accuracy. Implement deterministic automated test suites, execute code in secure execution sandboxes, challenge outputs through counterfactual critique, and protect your workflows from context poisoning by ruthlessly resetting the context window whenever conversations deviate into circular errors. Fifth, uphold rigorous standards of data privacy, safety, and human accountability. Enforce enterprise zero data retention agreements, sanitize sensitive personal identifiers before transmission, construct multi-layered defenses against prompt injection attacks, and ensure that high-impact, state-mutating actions remain subject to mandatory human authorization. Artificial intelligence must amplify human capability while preserving human responsibility. Sixth, drive your applications forward along the evolutionary continuum from standalone prompts to structured workflows and autonomous agents. Decompose multi-step objectives into modular pipelines where deterministic software handles logic and databases, while generative models handle semantic transformation. When deploying autonomous agent loops, protect your systems from compounding error cascades by implementing secure sandboxes, rate limits, and cryptographic human sign-offs. Finally, continue your professional development by engaging with official educational ecosystems. Whether you build developer-centric software through OpenAI and DeepLearning.ai, architect enterprise cloud infrastructure through Microsoft Azure AI credentials, master multimodal intelligence on Google Cloud, or lead enterprise governance with IBM, grounding your skills in structured, verifiable learning ensures long-term career resilience. As you integrate these principles into your daily engineering practice, remember that true expertise is characterized by discernment and deliberate architectural design. The amateur sees artificial intelligence as an infallible oracle. The skeptic dismisses it as a novelty, but the systems engineer understands it as a sophisticated, probabilistic computing substrate. You know how to shape its probability landscape through precise context curation, how to constrain its execution through deterministic code wrappers, how to verify its outputs with zero-trust rigor, and how to govern its capabilities with ethical clarity. The future of software architecture belongs to those who can seamlessly bridge the divide between deterministic computation and generative intelligence. You are now equipped with the mental models, technical vocabulary, and practical blueprints required to build resilient, trustworthy, and transformative systems. Artificial intelligence is transforming every facet of the global economy, but its ultimate value depends on the rigor, curiosity, and critical thinking of the engineers who guide it. Continue experimenting, continue building with precision, and continue thinking like an architect.